review at this point. We had an average of 32 the first day, 25 or 26 on the second, 23 on the third, and now we have about 10 students remaining. So the course is so good that people really wanted to come back. At any rate, yesterday we covered a lot of modification of the traditional RCTs and the RCTs, the randomized clinical trials, but I couldn't cover the whole material. We ran out of time a little bit, and I would like to recover some of it this morning with 30 minutes on a few designs that we are supposed to cover. If anything, just for your information, is very critical. Yesterday, we showed you the traditional randomized clinical trials, and then we went in detail on wedge design, rollout designs, which are very important for public health practice if you want to do community intervention, community trial. The other important design is a cluster randomized trial, because then you can do to different settings, to communities. You can allocate communities randomly, or you can allocate clinics or hospitals or wards in a hospital or whatever. It's things, and there are subjects inside those things. These are the clusters, those nested type of design. So you also saw that, the cluster randomized. So I recommend you to review this material, go back to the literature I'm giving to you, cluster randomized trials and wedge designs, rollout designs. It's what makes feasible and possible to do randomized trials in general population in a way that's ethical and that's logical, cost effective, and you need to understand that. So we covered that, not so well, but we did. However, we had no time to show a little bit of difference in different type of design, regression discontinuity design, and more important, the pragmatic clinical trials, the concept, at least to have you understanding some of the relaxation of those incredibly strict rules that I gave you in the original 1.5 to 2 hours lecture on RCTs, or randomized clinical trials. So I would like to cover a little bit of that with you so that you don't feel like you didn't do justice to what we're supposed to do. But before we even start that, there's a lot of more material you can read on this lecture. I would like to just highlight to you about how important it is not to always be in this paradigm of randomized controlled trials. You know, that natural experiments are the main thing sometimes, and the only way we can do things. I didn't have much chance to show you natural experiment, but I showed you yesterday one example of a design that was created to be a randomized trial with a rollout design, wedge rollout design, but in practice it became a quasi-experiment. What do you mean by quasi-experiment? We did not have the randomization, but if you have a chance to read that paper, you're going to see that some of the natural occurrences and how the program was rolled out actually in the population kind of a mimic on randomization. It's not perfect, it's not ideal, but something. And I would be amiss if I don't mention and showed you the Pope of Epidemiology, John Stowe. He has a great pub in London that I drank a lot of good beer there with Dr. Ramos, who's the coordinator of this whole thing. We used to study together back in 85, 86 in London. At any rate, he was invited, or maybe tasked, to take care of the cholera epidemic in London in 1852. And then, you know, he was very meticulous, very good at data at that point. So all he did was to display geographically the cases of cholera in London, okay? And he found they're clustering for sure. And make a long story short, you can see cholera death at the red dots, and the blue is the water pump. And somehow they cluster more around the pumps, the water pumps. So that's it, you know. He didn't tell people to drink this or drink that. It's just observed. It's an observational design, but sometimes it's the best natural experiment. So he noted the cluster, and then he said, what if, by the way, he was also a pioneer of geographical software. Back then, there was those computers, right? So they have to draw this by hand and precisely. Well, luckily, a city of London had a very structured government system that had the people to do that. to have the streets well designed, and you can see that not all are lined up perfectly because they actually are very realistic. But that's geographical software. You basically display the occurrence on a geographical term, and you find a geographical cluster. Okay, so took that data and put together in this simple thing, because he noticed the clustering of the cases around the pumps, and he said, are they the same pump? Because, you know, today I wouldn't think like that. Maybe I would, but back then they know how the water is coming from, and there are only two companies. Say, well, maybe we need to look into that. The main two companies here in the remainder of London, see how they work. And he displayed the data like that, and that gives him the idea that there was something wrong about one of the company. All he did is to estimate the number of houses, the death from cholera, and the death in each of 10,000 houses. And you can see the Southwark Vauxhall company is 315 per 10,000 houses. Okay, why he would not do it per person? Because a house may have 1, 2, 3, 4 persons, right? So he did by house. You know, if you take an average of 3 people in a house, you can calculate to an instance density. But that was sufficient for him to be able to write this, and I wanted to read to you because it's so amazing. He said, the mixing of the water supply is one of the most intimate kind. The pipes of each company go down all the streets into nearly all the courts and alleys. A few houses are supplied by one company and a few by the other, according to the decision of the owner or the occupier at that time when the water companies were in active competition. In many cases, a single house has a supply different from the other side, meaning the same house as Vauxhall or have the other company, Lambert. Each company supplies both rich and poor, both large houses and small. There's no difference either in the condition or occupation of the persons receiving the water of the different company. It is obvious that no experiment could have been devised which would be more thoroughly test the effect of water supply on the progress of cholera than this. So when you do your randomized control trial, the first table you produce is a baseline assessment of all the things you're interested, plus everything else you have your hands on, to make sure that the two groups, the treated group and untreated group, are identical on everything except the intervention, except the outcome, if it is the case. That's what he was describing here. It's like a perfect experiment. If the devil wanted to do a perfect experiment without doing a randomized control trial, they would have done cholera in London, because the way the historical development of water supply, think about it, not only the water supply, one side of the street with one company, the other one side of the street with the other company, you could see contrast, but also inside the same house, because people are different quarterly, you know, there are people living, dwellers are occupying one part of the house, the other occupy. So in the same household, they will have people with color, people without color. Okay, so that's what randomization does. He had it without randomization because it was a natural experiment, even though it was a cohort study. What he did a retrospective cohort, by the way. Anyhow, let's go back to what I wanted to show you yesterday, but I ran out of time. It's important to understand at least the concept of pragmatic trials, and put a little bit of the history there. Schwartz, in 1967, he said pragmatic trials should be created to answer the question about decision-making clinical care. You know, what sort of care do I need? Because, you know, the randomized thing doesn't give me that. Explanatory trial, causal research hypothesis, biological and chemical process. That's okay, but it doesn't help. Trials should be designed to answer a question about clinical care, not about what caused the disease only. So he was looking for something else, not etiological research. And he thought that the kind of research we do for etiological research or for treatment, you know, clinical trials wouldn't do any good. And he was right, actually, about clinical care. Martin Rowan, well, should be, I'm sorry, I think it's 1977. Could this intervention possibly work in the real world in uncontrolled conditions? This is me. He thinks like me. Okay, that's what natural experiments are made for, or pragmatic trials could do for. Could this intervention possibly work in ideal control conditions or in no ideal control condition, or work either way? I will only know that if I do a pragmatic trial. So these are the kind of the reasons. I'll get you the right number there when I said I'll get the right year. You don't get fooled by that. At any rate, you have here a kind of a triangle of what's so-called explanatory trials and pragmatic trials. What they mean by explanatory trials is etiological trials, the one that trying to be as rigorous in internal validity as you can. As you remember, I didn't cover that. It's about bias, but internal validity means internally I can say in this sample, in this study, there's no bias. That's internal validity, very strong. If you have absence of bias, you have a high, very high, strong internal validity. However, if your experiment is so perfect, is so contained in a vacuum, object of any problem, it doesn't really reflect the real world, right? So it lacks external validity. So in the end, what pragmatic trials are trying to find is a little bit of a balance to bring back some of the external validity, so that if I find a result or an effect of an intervention or a treatment, I can actually easily extrapolate to other populations, and likely you'll be acceptable, likely you'll be available, likely you'll be reachable, likely you'll be used, likely you'll be utilized, and therefore the total impact identified through an efficacy trial will be able to be reflected as an effectiveness type of measure. Okay, so that's the whole thing. I'm not going to take much except to show those contrasts between them. An explanatory trial, like I said, narrow eligibility. Remember, have eligibility criteria, trying to restrict strict instructions, not only about the design, but whoever's implementing in the field. I remember I told you, do not do the randomization before you are sure that all participants are in. So there's a lot of rules, blind, control, placebo, a lot of details, expert practitioners, frequent follow-up the visits, surrogate outcomes, measure very closely, monitor, and intention to treat plus protocol. You don't analyze data if neither conditions hold. You need to do intention to treat and protocol and by protocol. Whereas the pragmatics, just a relaxation a little bit of those rules, a broader eligibility, flexible interventions, typical practitioners, not the expert, not the epidemiologist, medical trained guy who's going to implement the study. Is the guy who's doing this in the field, is the doctor, the nurse, the people. They're the one that are going to not only take care of patients if it's a trial involving patients, but they're also going to do your study. They're going to implement for you. You don't have research nurses, okay? You have just normal people doing it. No follow-up visit, objective clinical outcome, usual compliance, and intent to treat still remains, but, you may relax. So does it mean, for perfectly good practical reason, another trial might prefer a wider patient group, an alternative set of practitioners, another usual care comparison group, a proxy outcome, a shorter follow-up, and so on and so forth? You can always find justification for not following exactly. And here's a very interesting diagram I want you to review with me quickly, but then I'm having a hard time reading. Give me a second, folks. This is too small. I can't read this. Yeah. Sorry. So the pragmatoscope, and it's very interesting. A very explanatory trial on the left, a very pragmatic trial on the right. You can see those lines, So look at follow-up intensity, meaning the closer you are from the center, the tighter you are. And the open curve means, yeah, I'm accepting a lot of stuff. 10 maximum 50 points, 50 or maximum 50 points. So in a pragmatic trial, you hitting all those things in a very relaxed way. And I'm not sure if you'd be useful to go over a whole lecture on this, because it does require a whole lecture. But I left you a paper there that I did with Dr. Ramos, actually, which is a pragmatic trial. It has some of the relaxation. I want you to identify those relaxations of the rule of RCTs and see if you can tell me at any time you want to do it. At the end of the day, tomorrow, a month from today, I'll respond to your email, okay? But this is pretty much, look at this eligibility criteria. You know, if it's very tight, not that many people will be able to participate as compared to the other one, to the pragmatic here, which everybody can. Flexibility of comparison intervention groups, participant compliance. So you got the picture. So there's also the three of the forest. The three of the forest is the practice 10 domains and the pragmatic trials across domains. We already have that. You have that here. Maybe there's no exactly 10. I think there's 10. That's what we're using in that pragmatic scope. And the main points here is that, so when you do eligibility, who is selected to participate in your trial, you know, you need to know that to be perfect, you have to go one way, and this comes with experience, but also to the subject matter of expertise that you have and what you're interested in. For instance, if you're doing a study on death, you know, out of like you described it yesterday, worsening of the ADL, activity of daily living, in a cohort of older people. It depends on the age group. If you include a lot of younger people, like 55 and consider old, I may wait 15 years to see them die. So your inclusion criteria also improve efficiency, what you're trying to measure. And therefore, you should have calculated that in your power and sample size. So that's why you say, no, I want to accept only 65 and older, because I'll have a small chance based on my expectations here. I look at the data in the state of São Paulo. I look at the data everywhere. And it looks like I will have, out of 1,000 people, at least 5 deaths over the next 5 years. And my power says need to have at least 5 deaths. If the power calculator say you need about 10 deaths, you may increase your age group to 70 and get the same 1,000 people. So that might get you the trick. But in a pragmatic trials, you may be able to relax that because you would accept a low power perhaps or something like it, okay? Recruitment, how are participants recruited to the trial? Usually there's a protocol that's very strict in a RCT, but here you could accept the clinic sending people to build your trial. It's similar to the idea of the fixed cohort and a dynamic cohort, you know, study where's the trial being done. Usually when you do a randomized clinical trial, you're trying to do it in a very sterile, organized kind of clinic. You train everybody, everything you're saying. Here you're doing in the real world. So there would be a little bit of you know, maybe a record will be lost or something, or maybe. So it's a real world. And you can train as much as you can. The people in the real world, they will make mistakes on a frequency that's higher than the people who are trained to do research, okay? So in America, it's very common to have, we are an academic medical center, meaning my university, my medical school owns 5 big hospitals actually, but one of them is the big one. So we have a lot of people trained to deliver care, but also have a lot of nurses and researchers who work in the floor in a hospital setting. They are helper of research, and therefore they're trained to do research. And there's also a clinical trial unit who helps to collect data in the hospital. So you see the difference between where is the trial being done? Compare that to a hospital that the doctors have the right intention, have a need, they have the right type of patient, but you're not trained. I need to do a trial there. It'll be more like a pragmatic trial because I cannot have all this organized data collection, so to speak, okay? What experience and resources are needed to deliver? It's really related to the setting. I kind of covered that. Flexibility, delivery, and adherence. How should the intervention be delivered? Okay, well, if you have a clinical trial unit like we do, oh, it's perfect, okay? If the medication has to be delivered to patients in such way, and so on and so forth, everything is going to be to the T, perfect. But hey, how should the intervention be delivered in a rural hospital? With people working, they have to take care of patients, still have to help your research. Yeah, you be variation, and you better sample, do a kind of a validity study on top of it to see how bad the delivery was, how bad the adherence was, how bad the missing of data was, so you know how much of that may be creeping and creating bias in your study. Not on purpose, but just by the nature. So instead of just having your trial, which is not going to be a perfect, it's going to be a pragmatic trial, but you can do simple things like, sample a few days in a week to see how people are doing it, okay? It can be just observation, or even you do a scientific step, just go and see if that's creeping in. If you do a sample, is better because you have actual numbers to play and to do sensitivity analysis later on, because you know those type of mistakes are contributing to lack of information, which is misclassification bias, or to allow or impede a patient to be enrolled in a trial when they should have been enrolled. But at least you know what type of patient you sample was missed. So you need to create those kind of a control, quality control on the side to do a pragmatic trial, okay? So that's the drawback. Follow up, how closely participants are followed up. Same idea of flexibility at delivery and adherence. It's like people not doing the right thing, okay? Primary outcome, how relevant is to participants. So the people who are implementing your research as well as the patient, they may not be as motivated as the one in a randomized clinical trial. There was enough structure, very strong way to impress on the patients, the participant, as well as those who participate as collaborators on the study. Primary analysis, to what extent are all data included? And you need to be aware that you're going to be losing some of the data that you have initially in a pragmatic trial. There's a little bit more about it. The 9 dimensions for assessing the level of pragmatism in a trial. This is actually the Precis 2, and I wish I could read this, even with my glasses up. I'm sorry, I put a slide that you may not be able to read, but it's the same thing. How different is the flexibility in how the intervention is delivered? Yeah, it's the same. It's just a little bit more elaborate than the wording. So in here, I basically go about each of the issues, but I already described it to you a little bit. Just going strolling quickly, see if it's something that really caught my attention that I need to tell you. Intervention delivery. Read this carefully. This is a randomized controlled trial of all the Brazilian that I mentioned to you. If you have, you can see my notes on the bottom actually. Luiz and Chester, check that value is still correct since the editor changed from 3 decimals to 2 decimals. So this is even before being published. By any rate, so look at that paper. It's a pragmatic trial. You're going to see there are some things missing there for the traditional trial. And I didn't claim it wasn't. And here's some of that results. Nature kind of elaborated on the cohorts we were following. We're trying to create an intervention on the top of a cohort. And you end up with things like that show clearly there was an effect, but it can be questioned. That's the only problem with the pragmatic trials, because you are drawn to bias that is supposed to be taken care of by the randomization. So you always pay a price. However, think about this. If your magnitude of your effects is very large, like this one here, I've even forgot what I was measuring here, but there are 3 groups, intervention groups. And clearly this group here on the top, which is the CRG, whatever value we're measuring, let me see, average minutes per week. I think it was physical activity, right? Luiz, and this one, yeah, physical activity among older people. So you can see huge difference between that group and the lowest group possible. At the end of the period, this is over time, cohort baseline, pre-intervention, post-intervention to 0, 4 measurements over time, okay? And you can clearly see that this intervention at some point start kicking in, goes up and stay up pretty decently. I mean, it doesn't go down too much. The others went a little bit higher, but not much, and so on and so forth. So when you have effects like that, think about it. That's when you need your sensitivity analysis. The pragmatic trial is not perfect. Maybe there's some bias. Maybe in this case, I think there's a possibility of misclassification of exposure, actually, or the outcome of physical activity. So you want to play with the numbers and say, okay, what if all these people who are saying this is actually saying something different? Okay, you can do a lot of things to improve, but the fact of the matter is when you have high numbers, like very large magnitude of the effect, okay, the difference between the 2 groups is very large. It's very unlikely the bias alone would explain that. It has to be incredible bias, so obvious that people would see it. So that would be your best solution. If the numbers are small, you have, for instance, relative risk, which are hovering around 1, still not significant, not insignificant, significant statistic, let's say 1.1 to 1.3 or 1.4. That's very close to 1, which is relative risk of, that says there's no association between this putative exposure and this outcome. Then, the pragmatic trials maybe question the results, rightly so. But if your pragmatic trial gives you a relative risk of 7, like many other trials out there for different things do, even if it's pragmatic, I believe it, because bias alone could not explain such a multiplicative effect. Okay, this is a little bit of that. We also did not cover the difference in difference, and I wanted to remind you this is also used. So what I did is not only I mentioned to you studies, but I also showed you that it's doable. We did it, and you can review, you can criticize. Not perfect. We're not perfect scientists. We do what we can. We're pragmatic scientists. We're prone to do pragmatic trials instead of just watching and say, hey, I can't do anything about it because it's not doable, a randomized control trial. So I'll do it anyway. So difference in difference are not the type of research design that's not an experiment, it's not randomized, but it was very much in use as a quasi-experiment usually. It can be done as a randomized design. It's very much in use by health economists for economics, or for economics in general, for economic development, but very little use in public health practice. And about 13 years ago, I designed that study. I had many people better than me who better improved the design. And we use the difference in difference to study the impact of the Romney care, which is the healthcare system, which is exactly the blueprint for Obamacare. Obamacare is an imitation of that, 1,000%. Okay, if that's such a thing, I thought it's certainly imitation of that. So evaluate using difference in difference. So difference in difference combine two counterfactual before and after comparisons in comparison between those who choose to enroll and those who choose not to enroll. Meaning I did not randomize them. This came naturally, okay, before and after comparison. So I compare the treatment group before and after, and I compare the other group before and after, and I compare the difference between them overall and over time to produce a better estimate of the counterfactual, and I did not explain to you the counterfactual, but counterfactual, if I could estimate an expected value of the same person by experimenting two interventions in the same person at the same time, okay, which is not possible. So it's there in the lecture. You read it, you understand. I put some math, but it's not too much, and you can see it's before that point in this lecture, there's a little bit of explaining what counterfactual is. So note that the counterfactual being estimated here is the change in outcomes for the comparison group. Here's what the real deal happened. So difference in difference before and after outcome is Y, okay, for the treatment groups A and B, okay, why the outcome for the comparison group goes from C before the program to D after the program has been implemented. So B minus A, C minus D. So you can see that. I'll give you an example. Two counterfactual, the difference in outcome before and after the intervention is B minus A, because before is B and after is A. So I use names or letters that make it simple. So it's before and after intervention. And the difference in outcomes after the intervention between the treatment and comparison group, I call B minus D, okay? Because it's between treatment and comparison group. So the difference in difference becomes then B minus A minus D minus C, which end up being B minus E, where E is supposed value of B if long-term trend of comparison group is applied to the treatment group. I don't know what the randomization could give me, but I know over time, in a line, it would have given me that. I want you to read, it's too quick, and I just wanted to know the concept at least, and usually present something like that, and I did the Romney healthcare for you. The difference in difference met prevalence of healthcare coverage after the implementation of the program, okay? So you have B, A, D, C, C, A, B, C, D, B, D, A, C. This is not your 2x2 table, folks. This is something different. Okay, before and after, okay, D and C, comparison modify, and then you have your difference in difference. So you got the Massachusetts, that's the intervention. group, you got New England, which is the whole area around Massachusetts. That's not Massachusetts, and include Massachusetts. Okay? So you can see that in Massachusetts, the difference before and after is 5.2% prevalence change. Okay? Whereas the remainder, where the program was not in effect, was only 0.7. And the difference, okay, between these 0.5, between them, you know, between the before groups, the two before groups, and the two after group, the difference is 0.5 and 4, which give me a 4.5 based on that formula I gave you before. So here we go. I plug the numbers. You can see, but here you go. We already see some effect. You say, okay, 5.2. That's huge compared to 0.7. Then here you have a more elaborate from the regression, the difference in difference method, mental health on healthy days. This is different than the other one. The other one just prevalence of healthcare coverage. This is a mental and healthy days. If you read the whole paper, you fully understand how this design is done, how the numbers play out. And I think it's a very useful. I wanted to show you the rollout design, the cluster randomized design, and this design, just as an information, because you may need it. In public health practice, very seldom you're going to do a true, perfect randomized control trial. The situation, the setting does not allow you to do so. So, you know, this is a good halfway through, okay? So read this paper because it has all the nuts and bolts of that. And you can see the star there basically saying, hey, significant. This damn change here is big, okay? And the other one is these multi differences here. Difference at P value at 0.001. That's very small, okay? So this is an example that I want you to remind you. That's one way to present. The other way is just the first table I showed you on this thing can also be represented figuratively as a figure. And you can clearly see there. I mean, I don't need to be a genius to know that is an effect, you know, and I don't care if people say, oh, it's not randomized. Come on, look at the other place, you know, look at this one. These are prevalence changes. It takes years for prevalence to change over time, years for behavioral things, for things like that. Not going to mention the regression discontinuity because we have to cover meta-analysis. Read this all. I just wanted to go over with you, okay? Sorry for the intro too fast. It's 35 minutes, right? We went over. But remember those two designs. Remember the rollout design and the wedge design. And surely you have a full, nearly 2 hours lecture on randomized clinical trial. Everything you needed to know, and there's a lot of information there. Read those slides because they read like a mini book, okay? So let's go to the next lecture. I don't know how they're looking at. Can they see this there? That's what they're seeing.
Okay.
Still, yeah. Still sharing?
Still, no, you're sharing the other one.
Is that right? Still showing the other one, right?
Yes.
So you have to share the screen again. Sorry, folks. We'll be right there.
Yes, this one, right?
I believe so. Okay, let me see. Yeah, overview of meta-analysis.
That's it.
Okay.
Hide here.
So we are back to the supposed to be first lecture of today. We're supposed to give you only 2 lectures long. They're long. And this one, I made the best effort possible not to use formulas or numbers and explaining meta-analysis through words, okay? And you have to bear with me. This is actually created by Dr. Simões with a lot of freewheeling modification by yours here, okay? Dr. Simões was supposed to be here. I should have mentioned this to you before to give that part of the course to you all, but he had some health issue with family and he had to stay behind. But this lecture is all about concepts. And if you understand that, it'll be easy to look through the math, okay? There's very little numbers, or I don't think I showed any, maybe there's 1 or 2 formulas, but not much. So what is meta-analysis, why we do it, how we do it? So let's read this definition here. Feel free to understand the whole concept. Meta-analysis refers to the analysis of analysis, the statistical analysis or a large collection of analysis results for individual studies for the purpose of integrating the findings. It connotes a rigorous alternative to the causal narrative discussions of research studies which typify or attempts to make sense of the rapidly expanding literature. So this definition is basically saying we read so many studies on a topic, let's say diet and coronary heart disease, okay? And so what's the truth about it? You know, and some studies come out say, hey, if you eat this much, you're going to have a heart attack. And the other one say, no. If you eat this other thing much, you got a heart attack. The other comes say, no, that thing was wrong. So what's the truth about it? And the press makes a lot of noise, and we all make a lot of noise. So meta-analysis is a way of summarizing all that information and trying to find the truth out of it. The main purpose of meta-analysis, my understanding, is actually to increase the power of good studies that do not have enough power. Power statistically. I'm speaking statistically. So underpowered study is a problem in epidemiology. And much of it is coming because they're not well planned, one, or that's a problem with pragmatic trials or observation design. You don't control the elements, so you end up with less than you wanted to start. But if you do a good study on the sample size required and the power analysis, and you're careful with your losses, okay? So if you're going to get only 10%, not 90%, not 100% of people are supposed to be, you discount that, okay, in your calculation of sample size. So underpowered studies give you indication, what I call direction of association, but they don't give you the magnitude of the association that's unequivocally clear statistically. And therefore, to me, that's the best point of meta-analysis. It brings back the power to your study. Let's say you have 20 studies all saying that if you do not eat enough vitamin D, or if you don't have enough sun, you have a greater likelihood of developing coronavirus, okay? I'm not even talking about randomized trial. I'm talking about observation design, retrospective cohort, okay? And the relative risk for that is 0.9 for most studies. Some include the null hypothesis of 1, some include the do not include, but absolute majority of them are hovering around 0.9. It's very close to 1, which is relative risk of 1 means there's no association. So you're not sure. Only one study did not include the confidence interval 1. All the other studies did include. But if you do a meta-analysis, you may see a little bit of the truth and look, oh my goodness, they're actually not hovering around exactly 9. It's just rounding up the numbers. They're hovering around 8, and the confidence interval is much tighter now, is 0.7 to 0.9, very clear across the study. So now we have more belief that this relationship actually exists and is a truthful relationship. It may be a bad example. We may see some good ones over there. When you come up with made-up examples, you may not have the best situation. So let's look into this order here. Identify and address important issues, systematic, qualitative, identify areas of agreement and discrepancy, quantitative, synthesizing issues, providing a recommendation of perspective. So what is, why we do it, how we do it. So objectives, examine etiological hypothesis, we discussed that already. Assess medical technologies. So that's another use of meta-analysis. I hope everybody's familiar with the word etiological hypothesis, right? Etio meaning the cause, the original cause. So etiological means I'm trying to understand what causes that thing, that outcome, okay? Assess medical technology, a little different, is assess how good the technology is. Could be just a treatment effect, a chemical or a drug or medicine or an equipment or an implant in your body. It's a medical equipment. Inform and evaluate public health policies and programs. It helps to initiate the decision analysis, attempt to gain insight from the exploding information from published studies in thousands of journals. You have limited time to read, interpret and synthesize data results, like I said. Provide a more objective summary of the literature. Point is, meta-analysis does all of that, and better than the original study, because it summarizes everything. It gives a perspective. And that's why in the National Institute of Health, it's considered to be the ultimate design. Because to have a perfect meta-analysis, you already have to have near perfect studies before. They're just underpowered for whatever reason, either because the association in nature is small, they exist, there's a gradient, but it's small effect, okay, or because you lost people in your study and you lost power, or because you didn't design too well, but you're up to something, you're after something important, okay? So a meta-analysis brings this all up, and in the gradient or ranking of qualities, study qualities, NIH is now ranking meta-analysis on the top of randomized clinical trial, if it is a meta-analysis of a randomized clinical trial, okay? If it's a meta-analysis of an observational design, you'll be on the top of the cohort studies. So bottom line is, in general, you would have something like correlation study. That's the lowest level of kind of a epidemiological evidence for causation, for etiology, or for effect, if you're talking about medical technologies. And then you come to a cross-sectional study that you're trying to come up with association, which is very similar to correlation. Doesn't do any good. I'll put them in the same level. Some people put one in front of the other. You only use cross-sectional for descriptive epidemiology. I use it analytically too. Otherwise, there wouldn't be a prevalence odds ratio, right? Anyhow, those are very weak measure of associations that you can extract from them, and weak by design, prone to biases of all types. You don't really trust it, but it raises the possibility of saying, hey, maybe this is associated with that. So it's a hypothesis raising and maybe hypothesis generating at the lowest level that you need to test it out with something later, okay? So that's, and then you come with a case control, which is a little bit better than these guys. It's a quick and dirty way of doing a cohort study, okay? It gives some good evidence, especially in some ideal situation, case-based type of case control study or case-based, a nested case control study may be as good as a cohort. Some people question that. But then you have the cohort, which you eliminate a lot of the biases that you have in case control, okay? And you have some certainty, especially about your exposure, about your risk factor. You know that. You are certain, so there's no misclassification unless you're crazy. You do a cohort of something you don't understand. But if you're doing a cohort about ADL, you know, expectation, I'm an aging researcher, I know very well how to measure, how to collect, and how to synthesize ADL. So cohort should be way better than a case control study. And then the next level of evidence is the randomized control trial. And then if you do a meta-analysis of a bunch of randomized control trial, hey, you got the cream of the cream, okay? You'll be on the top of the food chain in terms of evidence. So the level of evidence ranking for NIH goes from correlation, cross-sectional studies, through case control, observational designs, including cohorts, and then randomized clinical trials. Some people would say, what about the non-randomized trials? They'll be at the same level as the observational design. They'll be at the same level as the cohort studies, okay? I personally don't think they are the same level, especially when the gradient that I find, the magnitude of the effects measured that I found to be very large, I think they are more powerful than a cohort study because they're actually measuring something that's actually happening, not something that happened in the past as a retrospective cohort, or is some observation I'm doing that I'm limited in how much I can observe. When I'm really there in the field testing intervention with real world things and I find a huge effect, yes, there's bias there, but hey, that's powerful. I'll put them personally in between the observational design and the randomized clinical trial, okay? And then you got the meta-analysis. So in the ranking of the level of evidence today in the world of academic and especially NIH funding top research in America is the meta-analysis goes big. So need objective evidence to make public health policies. So many of the so-called public health policies for CDC, for the nation prevention, as well as the Department of Health and Human Service, for other areas of health in general, like delivery of healthcare to older people, which is funded by the federal government since 1964. Every older person older than 65 has one of the best health insurance in the world. That's called Medicare, okay? Or policies, general policy of healthcare delivery for the Medicaid, which is healthcare coverage for the poor. The poor in America have been covered for all healthcare since 1964. Yes, people say all horrible things. It's a big lie, okay? Obamacare was about including 8% of Americans do not have healthcare because they decide not to. They prefer to have a Mercedes than buy a health insurance. And that's why people complain. Say, hey, these guys are not poor. The poor, we took care of it in 64. That's Medicaid. These guys are driving a Mercedes and they don't want health insurance. Now I'm going to pay for health insurance to them? Question. So, but the point is, going back, I'm digressing here. Going back to a policy, those policies now can only be informed by meta-analysis. It's decided. It's like internal policy, internal guidelines. So the guidelines for that is you need to have meta-analysis. Yeah, when you don't have one, you still can make policy. But if you have one, they're going to look to that before making a decision, okay? Evidence-informed policy making a balance, the influence of subjective values, stakeholders, and institutional factors. It is one of the many factors that influence policy now in America. It may be twisted to serve political ends. I doubt if the science is good, you got a good meta-analysis. There's no politics that can twist finding. I don't think so. It helps policymakers understand how the policy affects different individuals and groups, determine risk, efficacy, and effectiveness. So you love to have something like that. If you have a chance as an epidemiologist, do a meta-analysis of something that matters because it elucidates so much in the field, okay? And it gives you this perspective about the issue that you didn't have before in 1,000 years. I've been reading a lot about diabetes and informatics, how informatics can improve diabetes. The day I did a meta-analysis, canvases everything about this topic, and we found the results, that's when I was really convinced. Because until then, there's so many papers in informatics. Oh my God, millions of papers, all repeating everybody's same study. They all having different findings. That's crazy. So meta-analysis does that to you. Overcoming bias that may be induced by traditional narrative reviews. This is in contrast to the so-called systematic reviews that are not meta-analysis, okay? So compare meta-analysis with a systematic review that's not a meta-analysis. I'm just doing a complete review of the literature, and I'm creating a summary of it based on my own interpretation of that. That's very different than a meta-analysis. A meta-analysis is not an interpretative review, it's a quantitatively based review of the truth, okay? Avoid meta-analysis, avoid authoritative pronouncements. Vitamin C and common cold was an authoritative pronouncement by Linus Pauling, who won a Nobel Prize. If there is an effect, it's so small that people are drinking vitamin C forever, and the cold is getting worse. Advocate for developing explicit guidelines for conducting meta-analysis or randomized trials and observational studies. Yes, results from meta-analysis can be reproduced. Okay, so because it's so technical, you can reproduce and you can be tested. Whereas if I do an epidemiological study with some group of people and I try to reproduce, yeah, I can reproduce the method, but it will be different patients, different people, right? Here now I can reproduce the meta-analysis because it's using those very same papers. And if I do a meta-analysis and I find the results by my statistics are a little bit shoddy, somebody else can replicate my meta-analysis with the right statistics and find different results and publish it. So it's reproducible perfectly, 100%. Let me remind you again what I mean by here, reproducible. If I do a cohort study, okay, of ADL, activity of daily living, as the outcome, and physical activity as the exposure or the risk factor or the protective factor in this case, okay? And I use a cohort of 1,000 older people here in the city of São Paulo and the Clementino village here near UNIFESP. And I finished my study 4 or 5 years later, published the results. Somebody can use my methodology, replicate somewhere else, but they cannot reproduce my findings because that's specific for that population of patients. So, and that goes for any study, any clinical trial, any cohort, any case control, any cross-sectional study. I cannot fully reproduce 100%. I can reproduce the methodology. On the other hand, if I do a meta-analysis of the effect of information technology, which I'm going to show you the result of it at the end of this whole thing, on A1C, okay? And I have my findings. Somebody can do exactly that. And because he read my paper and say, hey, there's a little tricky method here that you may not have done right, I'm going to redo the thing, because he will do exactly what I did, because he has the same papers. It's already published and the results are published. So I'm not reviewing, I'm not creating a study with patients. I'm creating studies of studies, and the studies have been published. They're fixed forever. The values are the same. So anybody can reproduce 100% of that meta-analysis, okay? That's a very important concept, because it makes strong as a policy issue, because people have questions, okay, let's repeat this meta-analysis. I test, and NIH does that. They test top scientists to do repeat of that meta-analysis. And they will do it, and they'll find that, oh, that's solid. You know, oh, there was a decimal. There's nothing. There was a decimal error. I saw my notes on the stuff I showed early on. So the 10 key steps. So here we are in the how to do it. Formulate research question protocol. Develop a search strategy to identify studies. We're going to go over that each. Select the studies. There will be a figure 1 always with a flow chart, explicit inclusion criteria, similar to those little figures I was showing when I was showing you all the study design, the different study designs. Okay. Assess study quality. There are many ways to assess. I'm going to show some relevant ways. There are other ways, but I'm going to show some. Extract relevant variables. It's called evidence table, table 1. We're going to show examples of that. Analyze the data qualitatively and quantitatively. Examine heterogeneity. I'm going to explain what heterogeneity is. Calculate summary statistics that summarize the statistics across all the different studies, trying to find the truth among them. It's almost like take the mean of the mean of the mean. Okay? Conduct subgroup and sensitivity analysis to make sure this thing is robust. Provide conclusions and recommendation. Here we go. This is your meta-analysis recipe book, so to speak. Oh my, already 1 hour. We're going to go over a little bit. You know what? I'm going to take a break now. I tell you why, because I give the extra for the previous lecture, the 35 minutes extra. It's going to be, it's better to start step 1 and go all the way to step 10, because this is the big part of the lecture. Okay. So we take a 15 minutes break, 15, to come back how to do a meta-analysis, okay? And I'll show an example in the end. And then on the third hour, we're going to be working on something else. Some of the math. It's scary. I have to admit that. No, don't go. Stay. I'll see you in 15 minutes, okay? Okay. No, it's toast. Video pause. Tá o volume, tá a imagem. Isso, start share. Aí tem que vir para aqui e ir para apresentação. Eu acho que eu já estou aí agora.
É assim?
É essa, mas ela tá aparecendo aqui também, é a mesma. Ou é essa aqui? Aqui, agora. Dá para tu olhar? Tu tem como olhar isso? E ver o que eles estão vendo lá? Okay. I hope everybody is there still. I have no way of telling. Can somebody check, please, if everything is okay? Because I came abruptly. We lost 3 minutes. Can you check through the phone and see if it's working? Is Michelle there? Can you speak to me? Where's Fred? I need Fred here. I don't know if they're seeing. Can you? Once I'm in a kind of presentation mode, there's no way of seeing the students or. Tá tudo certo? Okay, folks. So we're back to the lecture with 2 minutes delay. I'm so sorry. Is that? Can you confirm that, Maria, please? Okay. If there's something wrong, I need to fix it now because this is the beginning of the steps to. Okay, so this is how we're going to do meta-analysis. We're going step by step. You have to formulate a clinical public health question in terms of etiology and risk factors, okay? Diagnostic testing, performance, and you usually have some kind of measurement that you're interested in, okay? If it's etiology and risk factor, you're dealing with odds ratios, rate ratios, relative risk differences, and so on and so forth. If you're dealing with diagnostic test, you may end up talking about specificity, sensitivity, receiver operating, characteristics and things like that. Effect of an intervention, that's a little different. If you look at the impact, you're going to be looking to attributable risk or population attributable risk. And then you can also be interested in summarizing predictions and prognosis. Understand potential pitfalls in that process. Individual study results are the raw data. Meta-analysis does not remove source of bias that run through all the studies examined, okay? And that's why Simon wrote here, garbage in, garbage out. So your selection of this study is the critical piece, okay? So review is retrospective in nature, thus are potentially subject to the same bias that you have in your studies. Therefore, we need a priori and retrospective studies, meaning I can be introducing, we're equivalent to a selection bias by selecting the wrong paper or the paper with bad quality, but we're going to see that there's some ways of prevent that. Therefore, we need a priori protocol. The protocol is going to be critical. It has to be a priori, meaning you cannot modify as you go along. You cannot modify later on. Can you still see it? There was a little noise here. When that happens, sometimes the voice is gone or image is gone. Is that good?
It's okay.
Okay.
If I see any problem, I'll let you know.
Okay. So protocol development. Reports should specify protocol development in sufficient detail. Think through the key steps, in particular specify the research question and anticipate, we're going to give you an example, and anticipate potential nature and sources of heterogeneity. Okay? Heterogeneity is just differences across studies, all kinds of differences, especially with regard to the main measure of effect or measure of association you're interested in. So meta-analysis of randomized trials of BCG vaccine, that's an example. Is BCG effective? That's your formulate your research question. Is BCG effective against tuberculosis. Is BCG effective in infants, which is a subgroup analysis, a subgroup meta-analysis? How effective is BCG against tuberculosis, which is different? Is it effective? You say, what's the size of that effectiveness measure? How effective is BCG in infants? So it's a subsetting of that. In which group is BCG effective? If there's other groups beside infants, we need to explain that. Which strains of BCG are most effective? So now I'm not classifying the outcome, I'm classifying the intervention, and I can analyze that too that way. All these questions are fair questions in a meta-analysis, and it should be thought. Is BCG harmful? And there's ways of identifying that you can do a meta-analysis just on the harmfulness of BCG. Let's say, think about phase 2 trials, okay? Maybe the results were not conclusive, but you have 10 studies, and you need to know what the conclusiveness of that is. The meta-analysis will do the job. Should BCG be recommended for whom? That's part of your recommendation in the end, based on the data. That's both quantitative and qualitative, but the quantitative have a bigger weight on meta-analysis, okay? Examples of meta-analysis of observation studies of glycemia and heart disease. A primary prevention question, right? Is elevated glucose level predictive of future coronary heart disease event? What is the magnitude and direction of that association? What's the size of the relative risk? And is that positive above 1 or below 1? Is the association independent of other risk factors? Can you classically say this is independent? These studies evaluated this association between glucose levels and CHD over time, adjusting for anything under the sun. That's independent, meaning the finding is independent. It doesn't matter if I'm black or white, old or young, whatever, the association holds. That's an adjusted measure. Is the association independent of other risk factors? That's the question. Does the relationship differ by sex and age? That's a little different. I'm here more interested in saying, is that attenuated or modified by another variable, a third variable? That's effect modification or interaction, statistically speaking. More specifically, can lower glucose level reduce CHD risk among diabetics or among people without apparent diabetes, meaning they are prone to diabetes but not there yet, or they are likely to become diabetic? Okay, so that is a different question. It's not, is elevated blood glucose predicts CHD? No, the question here is that, can lowering glucose level reduce CHD? That's like what? That's a randomized trial, right? I'm looking for an effect. And I can lower glucose levels with a lot of medication. That's what randomized clinical trials do for diabetes maintenance or diabetes management. Whereas the second question could be an etiological question. Oh, I found out that really they are related. So when I treat the diabetic patient to reduce their glucose level, I'm actually preventing coronary heart disease, okay? Should blood glucose be used to screen the whole population? If you ask what threshold cutoff, that's a completely different question. Here we're talking about prevention. I'm talking about using diabetes glucose level as a screener for preventing, not only diabetes, but in this case, CHD across a whole population. So it depends on your question. You're going to set up your meta-analysis based on those studies. And you need to know that, the first question is elevated blood glucose predictive of future CHD. I don't need randomized trials. I need maybe a bunch of cohort studies or case controls, okay? On the other hand, to say, can lower glucose levels reduce CHD risk? I need a tight cohort of people that I intervene with a glucose lowering, blood glucose lowering medication versus group that doesn't take that medication, okay? And if I'm doing threshold cutoff for whole population screening, I'm dealing with something different. I better that have a diagnostic test for blood glucose that has high sensitivity and decent level of specificity, and the ROC is decent. We have a whole lecture on that, actually 3 lectures on this. I can't explain to you now, but review that issue so you understand what I'm talking about. That's a totally different type of studies, and they could be RCTs also. They should be RCTs, okay? Meaning randomized clinical trials, in which the treatment is not the treatment, is the diagnostic, okay? And what you're looking at is is whether, the outcome is a perfect identification of a bad glucose level. Okay. Meta-analysis of observation studies of dietary fiber and diseases. So here we explore many questions on glycemia and heart disease. What about meta-analysis of observation design of dietary fiber and diseases? The first one was a primary prevention question. Remember, primary, secondary, tertiary, and primordial, it's kind of a primary prevention. So meta-analysis of observation studies of dietary fiber, you can ask the question, can increased dietary fiber reduce the risk of chronic diseases? That's a very general question. And many, you can even do a correlation study here, but it wouldn't be good, right? I wouldn't do a meta-analysis of correlation studies, but likely observational design like case control or cohort. But it could also be already a part of a trial. Can increase dietary fiber reduce the risk of chronic disease? But it's too broad an outcome, chronic disease, to be effective, to be doing that on a randomized clinical trial. More specific, can dietary fiber reduce the risk of colon cancer? That's more specific, or heart disease, or diabetes, or just cholesterol, insulin, or glucose level. Does it affect the circulating blood levels of cholesterol, insulin, or glucose, giving fiber? So, what type of study can give you that? Case control, observation design, and even RCTs. How much and what type of intake? That I'm very detailed now. You can get that from observation design, but it's better you get that from a trial that you actually control the elements, and therefore you know exactly what the intake is. Because in an observational design of dietary fiber, you're going to rely on food records or food frequency questionnaire. And they are very good, especially food frequency questionnaire, classifying people in high intaker versus low intaker. But they are terrible at telling what the amount of intake is. You follow that? So to do meta-analysis using the right type of study, you also need to understand the subject matter a little bit. It so happened, and I've done in the past a lot of nutrition epidemiology. I think I'd be involved in anything. So in this case, the type of intake, if you do case control or cross-sectional studies and try to derive something like that, you're going to be relying on food frequency questionnaire. You cannot tell what the type and the amount of fiber you're having or something like that. So how big is the effect? That's different. If it's attributable risk or relative risk, you can get that from either studies or observational design, but you cannot get that from a case control study. You cannot. Remember, you cannot measure the true risk directly. You can indirectly come up with an odds ratio. Maybe you can make the case, but you would not be able to tell what the attributable risk is. Well, you can also estimate the population attributable risk. There's a formula, RR minus 1 multiplied by 1 divided by R. We'll get to that. Did you get to that? Oh, I left you in a lecture when we did these measures. I left you this part. We didn't cover, but it's there. Read it. You see that you can get indirectly to a case control, but it's better to do a cohort to answer that question. And therefore, the meta-analysis is going to use cohort studies. What group would benefit the most for increasing intake? So that's a subgroup type of analysis that you need to find studies, either observational or RCTs would do that. Is too much fiber harmful? Should dietary fiber intake be recommended to the whole nation? That is, for instance, if your recommendation is coming from a study that has incredibly powerful internal validity, that most of the effect, you're going to see that later on, is fixed effect. It's kind of hard. If it's random effect, maybe, or mixed effect type of, we're going to talk about that later on, it could be extrapolated. And pragmatic trials could be extrapolated because it reflects real life as opposed to a very controlled environment. So the point of these two things over here is for you to know that the subject matter, the type of question matter, it happened to influence strongly how you're going to create your meta-analysis. What type of study? If I'm doing meta-analysis of case control, meta-analysis of cohort, or meta-analysis of both, or meta-analysis of randomized trials, or meta-analysis of non-randomized and randomized trials, I've seen it, it's okay. Because the interest here is about an intervention effect, okay? And I've never seen meta-analysis including correlation study. I've seen meta-analysis including observation design, including cross-sectional design, and people were a little bit analytical in the way they approach creating prevalence odds ratio. I've seen meta-analysis, including those two. But you need to understand what the question is, where the type of study can give you that, so you can start doing your selection. Search strategy. Usually, I'm using very much what we do over there. We use Medline, Ovid, PubMed, GratefulMed, all ways of getting to the Medline developed by the National Library of Medicine, which is part of NIH in the United States, National Institute of Health. Embase is another huge database. Cochrane, that came from England, library. It's very powerful too. We use that. And you can use anything. In Brazil, there are many other great databases too. I used one that I can't remember. It was a big one here in Latin America. Search method, you need to really explore your mesh terms. I hope everybody knows about that. There's whole lectures on how to actually be good at that. I'm pretty good at doing that in Google. I have my students doing all of that great work in Medline. But believe me, I find a lot of great stuff in Google. I'm serious. I may have a method. I can do a whole method analysis using Google. Don't recommend that, but it's possible. Keyword versus full text. You know that you can use both to explore. Methodological filters helps a lot. Read about how to do search using data banks like that for literature search. Inclusion, exclusion criteria, you can do that in your search and therefore exclude a lot of stuff that you don't need because you may end up with 1 million papers. How are you going to clear that up? Okay, so you need to be careful with your match terms, keywords. In my case, I did health informatics, technology, type 2, diabetes. That was my first search. I was interested in the effect of HIT, health information technology, on type 2 diabetes. Okay, so that was the first set of what there are other that we did, and it was amazing. We're going to show an example here. But here, this is how you actually do your work. Excuse me, I have to, every time it becomes too slow. I hope you can read. Can you read it on the screen? This example, we have some Leviton. That's a meta-analysis in 2004. There are 559 publications identified to the Medline search. That's the first level, big search. 17 publications identified from bibliographies. Okay, meaning I found the initial search, and then out of the initial search and reading the papers, I found some other literature in their reference list that relates to the topic of my interest. So I added that to the group, so it became 576. See how that works? And then from there, 73 potentially relevant publications retrieved for evaluation, because 503 publications means over 500 publications were excluded because of the retrospective plasma glucose measurement, meaning they're not the ideal type of measurement, no comparison between people without diabetes or non-CVD endpoints. So the initial search here, I wish Simi could have pointed what word he used for the initial search, because it would be much more explanatory. But I think you understand the picture. He probably did something like, the goal here is, where's the search? This example? No, maybe it's the example of glycemia and heart disease. So he probably, CVD, non-CVD endpoint. So it's glycemia and heart disease. Probably wrote glucose, blood glucose, glycemia, heart disease, ischemic heart disease, and coronary heart disease, because he was really specific to those endpoints, and end up with too much. Never say anything explicit like comparison group was necessary. So he had to do it, and also the type of measure. But you can do by using what we call filters, and not only keyword, but methodological filters, inclusion, exclusion criteria to eliminate. He probably did some, but it's still a lot of papers to review. Can you imagine your postdoc students reading 503 publications? Whew. Usually at that level, you review the abstracts, and if there's a hunch that you need to go something deeper, you go. I don't know how he did it, but it's Leviton, so it's not him, so I don't know if we're talking about the same thing. So bottom line is he excluded that many because they didn't serve the purpose of the meta-analysis. I need a comparison group. It wasn't there, many of them. I need a perfect measurement of glucose plasma, some methodology that's reliable, valid, and accepted. or I need a CVD endpoint, cardiovascular disease endpoint. If there's none, we exclude it. Because the source, even though I put the word coronary heart disease and something, he picked a paper that has other endpoint, but also mentioned coronary heart disease, but was not the main endpoint, not the main outcome of interest. Therefore, it was excluded from the analysis. Out of the 73 included, 34 publications were excluded because the inclusion of people with diabetes, meaning I cannot have a study on the effect of glucose on coronary heart disease with diabetic people. He wanted to do that in a general population or normal population, okay? It was an exclusion criteria he created and did later. You could have done early at the stage, but you can do that. Use that. It's safer. You do that exclusion later after you read it, okay? He wants the persons to be in those studies to be the general person. He's only interested in the glucose level. It doesn't mean I am diabetic. It means I have variation in my glucose level, and I'm close to being high glucose person, but not necessarily constantly high glucose to become a diabetic. So you wanted to exclude that because you want to see what's the risk by having high glucose. But without diabetes means everybody who is diabetic already has high glucose. Continuous analysis, missing. So he wanted more discrete type of variable, didn't want a continuous analysis. Missing data to calculate standard error. Many of the papers did not have enough data to calculate standard error. Remember that I mentioned to you early on in measurements and how we do those studies in randomized controlled trial, that the ideal way to compare effect is to use a standardized measure as opposed to just, it's 8% one group, 2% the other group. The difference 6% divided by 8% is 66%. No, you standardize that, and you do that divide by this, the standard deviation. So you kind of standardize your measure. But to do that, I need a standard deviation, I need a variance. Okay, so if there's no variance, I'm excluding subsequent publication on same population. Meaning it was not the original, it's just a subsequent publication. Like you publish your paper, original paper, and you publish another one. It's just a slightly modification of the original one just to get more publication. People that do that trick all the time, but you need to go to the original one. 39 articles identified with prospective measurement of plasma glucose, not retrospective, CVD endpoints, meaning cardiovascular endpoints, and a comparison within the non-diabetic population. So you have a comparison group there. 30 populations from these papers extracted for categorical meta-analysis, 26 populations extracted for continuous analysis, and 13 populations extracted for dose response analysis. Okay, so summary of the article selection process. Number in parentheses denote those articles excluded due to respective reasons. We've gone to that, right? But there's a little bit more. This one here go for other reasons. For instance, irrelevant on the first level, photocopy and review of 135 papers. Irrelevant, case reports, letters, reviews, and editorials. Editorials is not a full paper with methods that I can extract anything. Reviews, same thing. I'm reviewing all the things, not my own original population. Letters, there's no data there. Rarely you can see data on a letter. Case report usually is unique for one case or two cases as case series, or irrelevant, they're not to the subject matter. Okay, that's where you end up. So that part was not shown here. Okay, but maybe this is a different, might be a different, it's Choi, it's a different study. Anyhow, detailed review, case series, excluded, and clear patient selection method and acceptable case definition. Unable to make contingency table at the final selection. I could not recreate a contingency table, a 2x2 or 3x or 2x or C by K table. Articles by the same authors to avoid double counting. Okay, so we eliminate the article from the same author on the same topic usually to eliminate double counting. Then you go to study selection, detailed eligibility criteria. After human, specific therapy, specific study design. Like I said, I need randomized controlled trial. Study design categorized such that analysis can be stratified according to the design. Okay, reject log recording omitted studies. So you don't want things that just mentioning stuff that was recorded and done before. You want the reflection of the truth of what the person who did the investigation, the PI, actually implement that study and have all the elements at hand. Quality assessment, review of trials for eligibility. Okay, double-blind, diagnosis, meeting, standard definition, patient group. If you want randomized clinical trial that are perfect controlled designs, you need to have double-blind, placebo clinical trial. And sometimes it's impossible to do that depending on subject matter you're interested in. Diagnosis, meeting the standard definition that you create a priori in your meta-analysis. And patient groups well-defined. Non-randomized study stratified according to design. If you want to include non-randomized design together with randomized design, you know, they need to be stratified according to the design, because the design becomes an effect, becomes a variable that you include in your analysis. Okay? Prospective cohort is one, case control is another one, and so on and so forth. We'll see how that goes when we talk about heterogeneity and if we're going to use fixed or random effect. Evaluating the fixed or random effects to analyze the data. We'll get to that. Evaluating quality of individual studies. Don't mix quality with precision, okay? Precision is about power, it's about having minutes. That's why I'm doing meta-analysis. And by having X number of studies, I'm already increasing the power, okay? Can be used as inclusion criteria, explanation for heterogeneity, and sensitivity analysis. So the quality of studies are going to help us to explain in the paper the inclusion criteria. It's going to help to explain the heterogeneity, and it's going to help to explain the sensitivity analysis and why I'm doing the sensitivity analysis. Okay, so quality is very key here. And I remember I told you the ranking of level of evidence. It's correlation, cross-sectional, case control, retrospective cohort, prospective cohort, non-randomized trials, randomized trials. Okay, so that's part of the quality, but there are other issues about quality, about data collection, about absence of bias, control of confounding, things like you can create a lot of items that you want to exclude or include studies based on that quality. It will help you diminish heterogeneity. It will help explain why you have more or less heterogeneity, and it's going to help to make decisions about sensitivity analysis. Quality scores, transparent and parsimonious. Don't confuse with quality of reporting, report scoring methods. So basically, you need to have scores of the quality. You create scores. I didn't in the studies. I just did a qualitative analysis of the quality of the studies because I have very specific criteria. I only want to randomize controlled trials. Well, that excludes a lot of stuff. It's already a measure of quality of the highest level. So within them, I eliminate some and explain why, just wordly. I didn't have a score, but you can create a score of quality based on a ranking of level of evidence, absence of bias, control of confounding. You can give a point to each one of them, explain your score, and then in the end, you sum up the score, say this studies that I kept hit this cutoff of 10 or more, and that score of quality, those were not the 10 or less, and I exclude them. Okay, that's what the score is, folks. You need to present that. Methods for extracting data is described to readers. What do you mean to readers? Well, when I go to that phase that I mentioned, I have 400, 500, my PhD students or my postdocs in my lab, they're basically saying, how are we going to do this? Well, everybody reads twice independently. And you guys need to agree. Okay, read the abstracts, read the method section, see if those things are there. And I have a protocol. Okay, so once they read it, they say, I conclude it should be in. The other ones say, I conclude it should be not. Then me, God, go there and say, hey, let me read again, the whole paper, and say no or yes, okay? But the two readers, that means, that's what I mean, two readers. Error checks, checking for error, adjudication by a third, that's what I just described, or a group discussion. If you have enough people, you can have a group discussion for those doubtful studies to be included or not. The best way to avoid that in data extraction, to have a quality score. Like I said, the two meta-analyses, I was directly involved. I participated in 5 meta-analyses, but this one, I designed them. It didn't create a quality score because we defined that our inclusion criteria would be randomized, control, placebo trial, okay, double blind. So you don't need a score, but you still could. And the explanation why I exclude some study or not is to explain that I excluded study that did not have the right measurement. Even though you do double blind everything, but you didn't measure right. Okay, you didn't measure something chemical with the right assay in a laboratory. So you exclude it. So that's how I do. But the best way is to create a quality score, especially if you're including a lot of studies which are not exactly the same design. Like I'm doing a review including RCTs, non-randomized trials, and observation design cohorts. Okay, so therefore I need a score, and the level of evidence will be a 1 score. It's going to go from 0 to as many. So cross-section, correlation cross-section is 0, counts 0 for that score. If it's a case control, counts 1. If it's a retrospective cohort, counts to 2. If it's a prospective cohort, counts a value of 3. If it's a non-randomized trial, counts a value of 4. And if it's randomized design, it comes to a value of 5. And if it's a randomized control design, double-blind, placebo, I give it a 6. So you have a score of levels of evidence. Then you do another score, and you sum up your score. Do another score, say data collection score, and say, did they do A, B, C, D? If they did all of that, I score so much, 5. If they didn't, only did this, that, 4, 5, and so on. Once you have your score, add them up and explain that to you. It's just extra work to explain in the method section of a paper, and you need to be very parsimonious how you describe that. But that helps you, because later on you need that for heterogeneity discussion. Data extraction, like I said, it's depend a lot on if you have a good quality studies at hand. Error checks, adjudication by third person, that's me. And always have to read a review. And the first review is this level here, folks. This level here. See that first line here going to the box? Okay, that's the first level review. You want 2 people reading, and you can do that throughout. Okay. So table summarizing key points of each study has to be created. Years of publication, study begun, so on and so forth, study design, experiment versus observation perspective. And you can create a quality score and describe that too. Characteristics of the study population, location, measure, exposure, covariance, and outcome. I'll show you a full-blown example. But here I have a little example already. Oh, that's a good one. And this is probably the paper we talked about before, the Choi paper. It looks like, or the Leviton paper. Okay, you can see here, I put the lead authors in the first table. The participants, events, how many people participate in events. Participants is the first number, and events of interest that you measure is in between. Events could be death, could be developing a bad ADL over time, could be anything, okay? For instance, this first one, interesting enough, whatever is the event of that study, I think is plasma glucose going crazy. It was only 1 out of 1,462 people. That's very unusual. Wow. At any rate, duration in years of the study, 12 years. Wow, what's going on here? Maybe I'm missing something on that event. Maybe something beyond just glucose level. Okay. It's hard without reading paper to tell what it is. But you understand the picture. You need to create this table and present that. Age and years of study participants. You see that? The ideal cohort, you have people similar age. This one looks good. They are kind of similar. They cross over each other, meaning in age. Even though I want to say 65 to 84, but then the other one, well, this one is a little bit off, 35 to 64. But most of them include people around the 50s, 60s. Okay, so outcomes a little different. I can combine them all in one bad outcome called CVD negative outcome, or just a focus only on mortality as a subgroup analysis, okay, or just incidence. But they're not exactly all of them have the same, but I took them all because they are talking about cardiovascular disease, okay? Coronary heart disease. And CVD is when it's a very broad, the original studies look at all cardiovascular disease, not just CHD, which is coronary heart disease, or myocardial infarction, MI, okay, or stroke for that matter. But in this study, all of them included, therefore, you analyze them all at once as a one outcome. You includes if CVD mortality or CVD or MI incidence or CHD incidence or CHD death and so on and so forth. It's all the same. Control for risk factors. Did you control for risk factor? Yes, no, 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 no. So this study here is control for risk factor, have large sample, very large population. So you can start seeing here, you having a sense of the quality of those studies. Plasma glucose measurement, fasting, post-challenge, fasting, HbA1c. Well, You see that? Fasting is pretty decent, but it's not the ideal. Post-challenge is really, because these are normal people. Remember, exclude, if I'm doing that study I just described before, when I did the selection, the steps of selection, if I exclude all the diabetic person, a post-challenge would be a very interesting and more powerful way to see if the person really, after the challenge, developed permanent high-level glucose, more permanent, but for a longer period of time than expected. HbA1c is even better because it's average. If average out, it tells what your average over the past 3 months of glucose levels. And it corresponds, there's a formula that allows you to correspond to find the value of glucose, average glucose based on HbA1c. Not perfect, but you can track back. So again, oh, where am I? I went too far. Give me a second. And the last one is the relative risk. You have all the relative risks and the range. I'm sorry, you have the ranges of the measurements. Okay. Sometimes over here already you put the standard deviations. Analyze the data, qualitative and quantitative. How am I going in time, folks? We good? We good on time? What time should I finish this one? Já dei uma parada. Não, mas eu ainda tenho uma outra aula para dar. Meia hora, não, meia hora. A gente começou. Yeah. Okay. Sorry, folks, I'm trying to check the time because there's a good material to cover. You're going to like it. I don't put any numbers, it's more about how to do it, okay? And there's a lot of definition I'm going to use. After you do those steps, you're going to see some pre-definition here. Qualitative, quantitative analysis data. Analyzing data. Describe, approach, and detail, present result in a clinical meaningful form. So I'm guiding you how to do this thing, present in a paper. But we're going to go over analysis, trust me. Qualitative assessment, like I said, intervention study, study type, RCT, cohort, case control. Hey, you know, you did a quality score, maybe you didn't. You have to explain that in your methods and your discussions about the quality of those study issues. Randomization, completeness of follow-up, blinding of patients and clinicians. Etiology, risk factor studies, like cohort, case control, type of associations. You're not dealing with treatment, no treatment. You're dealing with what caused what, and you're trying to find the truth about that, okay? The issues here are really about selection bias, confounding, and misclassification. Remember that? Selection bias, bias that you create, you scientists, when you design, create, by the manner in which you bring people into studies, your study subjects. Measurement error and misclassification, which are one-in-one, so to speak, because measurement error is going to lead to misclassification, but you can have misclassification without measurement error because you have a wrong definition. So misclassification is really we try to collect data on people and you misclassify them. You call them something when they should be something else. And it's very common when you have a situation when a clear cutoff on a continuous variable isn't there and you need to make subjective decisions about that. Okay, like let's say BMI, I have it because it's established what the BMI is to be classified as obese or as overweight. Okay. But let's say I didn't have that. I only have a measure of BMI. I have to make a decision what the cutoff is. Whenever I make that decision, a lot of people will be classified as heavy when they're actually normal. They're just Arnold Schwarzenegger, have a high BMI. Okay? So that's what I mean by misclassification can happen without measurement error. Effect modification, you need to explain that in your original studies. You know, what are you expecting? Reasonable evidence of causation and the studies. And you do the same with the meta-analysis because you just amplify what each of the original studies gave you. That's what you're doing in a meta-analysis. Okay? Quantitative methods and meta-analysis. This is the qualitative assessment. Your quantitative methods, you introduce classical quantitative methods for research synthesis. Fixed effect, random effects, mixed effects, meta-regression, graphic study, and S. The next lecture is going to be more about the mathematics of it. And I'm going to explain theoretical, but I have to show you a bunch of formulas. Here, I'm going to explain them, what they mean, wording, and examples, and you can understand. There's Stata can do all of these analysis, but also SAS can. And Bayesian and new development approach are actually even better. We're not going to cover that in this course. So what is random effect and fixed effect? Go back to your regression, linear regression, I use words. And I did an extensive search. It's not all of that's my own words, a modification of somebody else's words. And I saved the stuff. I didn't have time to plug that here, but I'll in the copy that you have, I'll put the citation so you can go to the original stuff and read it more in depth, okay? So fixed effect represent effect of variable they assumed to have. By the way, fixed and random effects, it's speaking statistically. Think about regression. Think about linear regression, okay? Multivariate linear regression, okay? And why would I need a fixed and random effect? And those two issues come in linear regression, usually multivariate regression. When you have, for instance, one example, when you sample from unit of sampling is a group, but the unit of analysis are the subject within the group, okay? Well, you have two levels of variance. Do these people inside the group, are they fixed within the group? Yes, that's the group is a fixed effect, but across them, they vary. And then there's vary also between groups. So you create different levels of variability, and you better use a random effect for that, okay? So let's see if we can get this to this statement here. Fixed effects represent effects of variable that are assumed to have a constant effect on the outcome variable, okay? Let's say you have an outcome variable that is a function of a treatment group, non-treatment group, and you have an effect. But you know that this effect is modified by sex or gender, right? So women will have differently because of the hormonal level they have for this specific experiment. Well, the effect of sex is a fixed effect. All is going to happen to all the women, okay? It's not a random, doesn't come and go, and come to one, doesn't go to the other. Whereas the treatment effect is random. So you have a mixed effect situation here, okay? While the random effect represents the effect of variables that have a varying effect on the outcome variable across groups or individuals. This is exactly the example I gave. Let's go a little bit more on that. For example, you could be studying the effect of exercise on body fitness in college students, where there's a fixed difference between male and female. But within each group, male and female, they share similar relationship with outcomes like muscular mass, okay? So the groups will differ on the effect of exercise, but within the group, they share similarities of the outcome. So they have variability coming more from the between than within. Another one here. When to use fixed and random effects in multivariate regression. When the feature or factors you're interested used in a model have fixed level categories like gender, age group, that's a telltale sign that you actually need to use a fixed effect model, okay? However, if one or more feature factors has only a limited set of categories and the model outcome is supposed to apply to for all other levels of categories, meaning those two levels are expressing much more levels, this could be a random effect or mixed effect model. I'll repeat again. When the feature factor used in the model have fixed level of categories, like gender, male, female, age group, young, middle age, old, the appropriate model, okay, is a fixed effect model. Because the effect of that on the outcome is kind of fixed by the group, okay? However, if you one or more feature or factors has only a limited set of categories, and the model outcome is supposed to apply for all other levels and categories, this could be a random effect or mixed effect model. A fixed effect model supports prediction about only the level categories of feature used for training. If you're doing, actually, this is interesting, I use the word for training, because you're now dealing with machine learning, deep learning. So, but the same things, if I have not used the word training, you still work for multivariate linear regression, because we use that in machine learning. A random effect model, by contrast, allows predicting something about the population from which the sample is drawn. So you want to extrapolate and be certain of your extrapolation, and you have mixed stuff fixed, and use random or mixed effect. Also, the random effect is more powerful in identifying or at least estimating, expecting through the estimation the right variance of the effect measure that you're trying to measure. I think I have that somewhere in there. Mixed effect models offer several advantages, or random effect. They allow for the inclusion of both, in the case of mixed effect, both fixed and random effects in a single model, which can improve the accuracy of the model and the estimation of the effects of variable. And the accuracy is improved because it does usually get the right variance, okay? Or at least it's a more robust variance. It may be a little bit larger, but it's better. Additionally, mixed effect model can handle unbalanced data, and data in which not all groups or individuals have the same number of observations, okay? More easily than fixed or random effects model. Okay, so the mixed effect can handle unbalanced data. In a fixed or random effect model analysis, you need the groups to have more or less the same number of people and the same number of observations if you're dealing with repeated measures on each individual. A fixed effect meta-analysis estimates a single effect that is assumed to be common to every study. So I'm reviewing a meta-analysis, 10 studies. So a fixed effect estimates a single effect, for instance, let's say the effect of whatever it was, I forgot, we had on glucose level, okay? So assume that an effect is common to every study. While random effects meta-analysis estimate the mean of a distribution of very different effects. I'm not assuming the effect is fixed. The other one assuming the effect is fixed. Takes an average, but assumes it's fixed in the analysis. The other one does not. It expects variability in the effect. Study weights are more balanced under the random effect model than under the fixed effect model. Especially using the mixed effect model, you have more balance of the weights. Heterogeneity in meta-analysis. It refers to the variation in the study outcomes between studies. That's pretty obvious, right? So when a study shows an effect that's big, the other one is much smaller. The other one shows a negative effect. That's a lot of variability right there. And also the other variables are also varying a lot. The way you measure the average is very different. In this place called StatDirect, I'll get you the right website for it in the lectures I'm going to send to you. Called Statistic for Measuring Heterogeneity in Meta-Analysis, Non-Combinality, which I thought interesting to give it to you because I never heard before. Meta-analysis, we call those statistics the Q and the I square. They call non-combinality statistic in order to help the user to interpret the results. That's what it does. Heterogeneity helps you to interpret the results. But it's also a measure of how much heterogeneous your findings is. If you do a perfect, if there are perfect studies out there, they're just underpowered. Let's say you have a perfect world. All the studies you want to review and do a meta-analysis, they're all perfect studies. Perfect randomized trials. Perfect, done perfectly, but they're all underpowered. The meta-analysis is going to tell you exactly what is going on. And the heterogeneity will be so little that doesn't even matter because they're perfect study. You're going to see very little heterogeneity, or the I square and the Q values, when I'll show to you what it is, are going to be non-important. But in real world, you don't have that. You don't have perfect studies just underpowered. You have a combination underpowered study, most of them are, and not imperfect studies and imperfect measurements, and you try to make them as look, you use them as and say to yourself, they're as close as possible. But hey, that group of studies show the table, CVD, mortality, CVD incidence, coronary heart disease death, coronary heart disease incidence, they're not the same outcome, but I assume they're all the same, okay? So when you have a situation like that, heterogeneity matters. I need to measure that, and it's going to affect how I interpret this thing. And that's why this guy called this StatDirect calls non-combinality statistics for the heterogeneity measures. Measure the inconsistency of studies results. There's the Q statistic created by Cochrane, which is calculated as the weighted sum of squared difference between individual study effects and the pooled effect across studies, with the weights being those used in the pooling method. Basically, he say, okay, let's say I have all the studies I've done, I got their means for the main effect, okay? And that's the pool effect. And then I have the between individual study effects. And I take the difference between individual study effects, each one of them in the pool, and the weight is the weighted for the pool. It's very similar to a Montel-Hansel statistics. and that creates a Q statistics, okay? And that way I can find out if this thing follows the chi-square distribution, because it's, the pool effect is almost like, with the weight is almost like a standard deviation in the denominator, okay? So Q is distributed as a chi-square statistic with K, number study minus 1 degree of freedom. So at thin study, it be K is 10 minus 1, 9 degrees of freedom, okay? The other statistic is the I-square. That's the one I use. Describe the percentage of variation across study that's due to heterogeneity rather than chance. So eliminate chance. Say there's a lot of random variability. I eliminate that. I focus on the heterogeneity that's not due to chance. Okay? And it's usually measured by 100 and multiply Q minus degrees of freedom you have divided by Q. I-square is an intuitive and simple expression of the inconsistency of studies results. Unlike Q, it does not inherently depend upon the number of studies, because Q improves with the number of studies. Remember, the variance diminished with number of studies. Okay, so with the number of things. So here's the same thing. So Q is just, I-square is just a better way of using Q and eliminating. Q is taking care of something, and I'm calling that that proportion. Q minus degrees of freedom I have to, the chi-square is going to tell me what the actual random chance is based on a chi-square distribution. And then I eliminate that. What is left off is the difference between that. That should be true heterogeneity across studies. So choosing between fixed and random effect model. If there's very little variation between trials, then I-square will be low and a fixed effect model might be appropriate. Remember what I said to you? If I have perfect studies, perfect, all of them, I'm reviewing 20 randomized clinical trials of HIT, health information technology effect on decreasing A1C among people who are diabetic. That's my study, okay? If all those studies were perfect, it's just underpowered. The meta-analysis will give them power, and the I-square will be extremely low. I could analyze random or fixed effect, didn't matter, you give the same result. Actually, fixed effect is the right appropriate model, okay? With fixed effect, so this decision to use random or fixed effect has a lot to do with heterogeneity, and I need to look into I-square and Q. I hope this is something new for all of you and simple to understand. Even if you don't understand the stats, you remember the steps. I got a Q that's not so bad. I got an I that's excellent. I could do a simple regression analysis here, okay, across all the studies. With a fixed effect, all the studies you are trying to examine as a whole are considered to have been conducted under similar condition with similar subject. That's the assumption. In other words, the only difference between studies, their power to detect the outcome of interest. This is exactly what I said in the beginning. I was ahead of me. So again, this is an important concept. To make the decision to present your data as fixed effect model, you need to be certain that heterogeneity is not a big issue here. And the I-square is your best measure, okay? You'll be very, very low. You present a fixed effect. You have evidence in favor, and you assume all the studies were conducted in a similar condition. Because what really affects I-square is the different conditions. Remember, I mentioned to you that studies vary a lot, how people collect data, how they measure. That's, and also if you, in the exclusion-inclusion criteria of the meta-analysis, you accept studies that have different outcomes, that already introduces a lot of heterogeneity. It's not even the fault of the original principal investigators of those studies. You decide to accept to combine CVD mortality with coronary heart disease incidence with this and this and that. I did, in my study, the outcome was change in A1C over time. So it's very specific. So I did not introduce heterogeneity based on the outcome of interest. But, didn't mean that didn't have heterogeneity. And I measured it was, I did random effect, but there was some heterogeneity left over there. Choosing between fixed and random effects model continue. An alternative approach, random effect, allow the study outcomes to vary in a normal distribution between studies. So assuming there's a normal distribution of variation across studies, many investigators consider random effect approach to be a more natural choice than fixed effect. For example, in medical decision context, read this paper. That's an interesting. I'm telling you here, if your I-square and your Q are very low, and you read those studies, because you don't read 503 studies, but you end up with 30 studies or 20, read them all, please, as a police investigator. Your students, your postdoc already select the best studies for you, use the criteria, stop, read every one of them, okay? So if you're convinced by I square and Q that there's very little heterogeneity across studies, and you read them and feel strongly, you can use fixed effect. But these guys are questioning, basically saying, for some things, it doesn't matter if I square is even low, too low. For medical decision-making, I want you to use random effect. Now, random effect, you'll be penalized because you always find the appropriate variance of the effect measure of the effect size. Why? Because it's random effect, but actually you pay a price because you have less precision to some extent. Situation in which difference in studies outcome are not readily accounted for by sampling variation within studies is the true heterogeneity. As I explained before, it's the I square does that job, remember, by taking Q minus degrees of freedom divided by Q, okay? So when I do that, I remove the chance attributed to the degrees of freedom, okay? And what is left is true heterogeneity multiplied by 100% as a percent of heterogeneity, 20%, 30%, 40%, 70%. So situation which the difference of heterogeneity is exactly that. It's not accounted for random effect. It should be assessed and reported. When substantial heterogeneity is identified, exploratory analysis should describe facts that account for it. So you should consider, actually, some people say, well, I want to include the quality score created based on quality of the study as a variable in the model. Okay, that way I'm adjusting for it. That's one way. Design. Source of heterogeneity. Let's look at that. Design is one source of heterogeneity. And RCT versus non-random comparison is going to create heterogeneity. That in itself may create very different outcome values for the effect of the treatment or intervention. A priori stratification by design is useful to prevent some of that to creep in, but it doesn't control completely. Study quality, studies of glucose, heart disease, I showed to you, those, some of them are not good quality, and the measurement, we have to eliminate so many. Some I left, but they're still doing a little bit retrospective measure, or the continuity of measure was not available. Degree or types of exposure, important covariates were not controlled for, potential effect modifiers and look at, some do, some don't. So all of that is going to create heterogeneity across studies. And therefore, when I have a situation like that, yes, random effect is the way to do the analysis, because it's somehow magically trying to adjust for that, to extrapolate for a larger population. Meaning I don't have the ideal internal validity I needed to have, and not magically, but random effect to take care of some of that heterogeneity across studies, which has different sources. It's not like saying the random effect analysis of a meta-analysis data is taking care of uncontrolled confounding in the original studies, okay? In this case, there's uncontrolled source of variability across studies. Example, streptokinase, Stanford publication, 1979. They look at streptokinase treatment and death among patients and across 8 RCTs through 1979. There are 2.7 deaths prevented per every 100 patients, with a confidence interval of -6.3 and 0.9. That means the prevention include the null hypothesis of no prevention, which is, remember folks here, attributable risk is 0, right? Because you're looking to attributable risk, how many deaths were prevented, okay? So, indeed, you need to do analysis, but even the analysis still gave evidently more evidence in favor of protection, okay? But still include the null hypothesis of 0, 0.1, 0.2, 0.3, 0.5, I'll do it 0.9. Substantial heterogeneity in those studies. Each trial reported mean time from onset of symptom to initiation of therapy. Early treatment should be more beneficial. Include the ratio of symptoms as a covariate in the meta-analysis. So once you do that, so what you did is reanalyze the data, understanding your heterogeneity, and the substantial heterogeneity is because they picked on this. The trial reported mean time from onset of symptom to initiation of therapy. So that's the time, mean time of streptokinase treatment, okay? Mean time. earlier treatment should be more beneficial. Therefore, hey, I need to include the average, okay? The duration of symptoms as a covariate in the meta-analysis, because the duration of symptoms is going to create a function called mean time from onset of symptoms to initiation of study. So if you include that variable, it might affect the analysis in a more practical way. It's a confounding across studies that have that. So once I do that, the analysis completely changed. Remember, it was 2.7 deaths prevented with a confidence of minus 6.3 deaths prevented, meaning 6.3 deaths prevented, to increasing number of deaths to almost 1 death more. Now, after I do this adjustment, I include the duration of symptoms, 20 hours, 3 days, 4 hours, 2 hours, half a minute, whatever. You can, once I include that as a control variable in the analysis, 5.3 deaths instead of 2.7, and the confidence interval is totally preventative. I prevent on average 5.3 deaths with a confidence interval of minus 1 to 10. At least 1 death was prevented here. It can be as high as 10. Okay, that's an interesting study to read and how they come up to the conclusion. They look at I2, and it was decent level of heterogeneity in that study. So they knew they needed to use random effect. Okay. In 1979, I don't know if they had software that could do that job. I came to the United States in 98-1, and I was using, yeah, probably. I was using Proc Mix. No, Proc Mix came a few years later. I use a macro created in SAS to do mixed effect analysis. Yes, they may not have had it. I don't know how they did it. But just controlling for this possible issue of quality of designs, there was an inherent bias. All of them, not the study itself had, but each one did. All of them did, because they're looking at the time from symptom to initiation of therapy. So once I add that variable, it controls for everything. That's a very powerful way to show that. What to do? Reports among study variants. Always report that. Stratify your analysis if possible. Graphical display. Regression. Remember the principle of good regression practice later. Choice of summary statistics. Measure for binary outcomes. Okay. Remember, there's not only risk ratio. You can do risk difference. Number needed to treat, which is just 1 over the risk difference. Risk difference is the attributable risk. Okay. And then 1 over the attributable risk is going to give you the number to treat. Risk reduction is 1 minus RR. Remember, it's exactly this over here, risk reduction. Rate ratio, you will know that. You are expert now in rate ratio, incidence rate ratio. Continuous measures, difference in mean, standardized difference in mean, effect size, and correlation coefficients. I did more of that because I was looking at A1C as my outcome, so it's a continuous variable. Okay? And I was standardizing that. I could present that the raw data as a real number was standardized, a percentage that's standardized. Considerations, consistency across studies, you real them. So when you write a discussion, you have mathematical property, you need to discuss about your method and the random and fixed effect, easy of interpretation. So quantitative meta-analysis, okay, we're going to take a break. We finish this. It's going to be only another maybe 20 slides, and then we'll go to the next one. It's a little bit more quantitative, but this one has a little bit more explanation of forest plot and things of that nature, okay? But the key parts you already understand is the issue of heterogeneity. That's what bugs and destroy meta-analysis if you don't take care. And if you don't know, let's say Stamper did not have that light and his head to say, ooh, you know, from symptoms to initiation of therapy, and that streptokinase is given. That's a function of the time duration of symptoms, right? So people may have symptoms way earlier, way not, and that affects the outcome of the disease because this thing may be preceding. Some patients are very sensitive, have symptoms immediately. So Stamper also is a good cardiologist. I know he is, or he was. I don't know if he's still alive. But, you know, and he knows that these things affect. So you need to have subject matter expertise on the issue to start thinking about those possible bias creeping in. Okay? We will take a 10 minutes break. 15 minutes break. Okay, and then we can go over the remainder of this lecture, go to the next one. Thank you. It'll be a great audience. Nobody asked me questions. Kidding you. We're not following. Are we following the cash like Are we following up, monitoring the question like we did yesterday? Yeah, monitor. Okay, so let's do, let's take the camera off. Estamos de volta. Vamos ver como é que a gente está sharing. Ok. Não, acho que esse aula está aberta já. Overview. Tem que ser essa aqui. Vou terminar essa aqui, que faltou um pedacinho no fim. Dá para verificar isso? Está funcionando? Ok, folks. Tá vendo lá? E voz? Dá para ouvir? Tá falando? Tá bem, ok. Então, a gente deixou... Estamos de volta, pessoal. Espero que todos estejam já de volta do break. Nós paramos exatamente aqui, né? A gente estava falando da Quantitative Meta-Analysis. It's a generalized stratified analysis. So for those who remember, I didn't have the time to go over when you did observational designs, cohort, and case control. We did cover some of case control, but not as much. But even in a cohort, even though it was in detail, or the randomized clinical trials, we did not review the nature of how to deal with confounding and effect modification through stratified analysis and things like that. I would needed a lot more time. So when I came to measure of association, I would have extended that lecture at about 5 or 6 lectures. Okay, so we're skipping a lot of steps here, as you may imagine, in such a short period of time. Therefore, even here, you know, we didn't have much time to appreciate how much of all these analysis we're doing, even in the meta-analysis, relate to some extent to what was done before. You're going to see a lot of the Mantel-Hansel type of weighting because meta-analysis is nothing more than a glorified stratified analysis across all the studies. And if every one of those have done a stratified analysis, you would have a stratified super-analysis. That's what the meta-analysis is. Okay, and then we already know how to formal test heterogeneity. We're going to see a little bit of the funnel plot, forest plot, scatter plot, a lot of things that visually allow me to see things, and have an appreciation for the fixed effect and the random effect through a graphical way. I want you to study, because again, there's a whole lecture ahead, and we need to finish this one. And even though I was told to, you know, give as minimum possible equations and formula, we still have to have some, okay? But I'm not going to discuss them. I'm just going to show you so you feel the appreciation of it. Here's a graphical representation of fixed effect model. In a fixed effect, you have one universal true mean. Remember, all the women are going to behave the same, okay? Where women, in relation to men, behave the same. Within them, they have variability, but not between them and men. That's the only fixed variability you see on average. Is the average of the mean for women, the average for mean for men. Okay. Then you have random effects in which, you know, you don't treat things like fixed. You know, they can vary within the cells. So you have random little curves around each of the possible means that you calculate. So this is like a graphical representation of what the fixed. Okay. You have your measurements in red. And you have this true mean, which is imaginary and theoretical. Whereas here, every one of those have his own little curve, and they together compose a bigger curve. And there's also a mean over there, but you don't know. And, you know, you can see this measure of variance has two levels. One is the fixed and the other is the random. And when the random is 0, then they converge to a fixed effect. If there's no random variability within each of the measure, then it becomes this. Okay? So the key difference between them is the choice of your weights. It looks like they look alike on the surface, but they come from a different strategy, and there's a little dot. So the expected value for the effect, so to speak, in a fixed effect, and the variance is what you see here. So look at the variance. They say 1 over the summation from 1 to whatever k levels you have across studies of the weight sub I. And on the other hand, the variance for the random effect is the weight sub I to the star, with the little star. And the little star means a complicated weight. Is weight sub I elevated to 1, which is 1 over, which is the original weight you had from the fixed effect, plus another component of variance. And both elevated to minus 1, so I mean 1 over this whole quantity. Okay? So that's the difference between them, is the random variability. It affects your variance. And you always find the right variance when you doubt to use a random effect, but it blows up because you have two components of variance. It makes the variance larger for the effect, so it's harder to find a true effect using the random effect, but it's a conservative way to go about it, as opposed to using a non-random effect or fixed effect variance. But if you have a nice square that is nearly negligible, nearly close to 0, I mean 5%, 2%, 10%, you could easily use a fixed effect regression to estimate your main factor, or main effect size, be it a relative risk difference, a continuous variable, percent change, standardized percent change, whatever you measure. Okay, a little bit more on the weight, different weights. Remember the rate ratio, that's the mental Hansel kind of a derivation over on the top there. Okay, the equal weights, the strategy specific person. This is really the reason why these things are all related. This is the variance estimation through mental Hansel view of a confidence interval for a rate ratio. Okay, remember there was square root 1 over A, 1 over B. It's showing here. And your weights is 1 over the variance of the log of the relative risk. So that variance of the log is 1 over A, 1 over B. And you take the inverse of that variance, that becomes the weight. Okay, and that's a mental Hansel approach to weighting. It's very similar to that. There we go. I talked to the master. He shows up. There's also something called MLE, or maximum likelihood estimation. Unbiased, computationally intensive, implicit, and all is possible. Not going to show it here. I don't even know how to show too much mathematically if I don't see it, if I don't study it again. But it's pretty complicated calculus to get to it. Direct standardization, it's just taking whatever is your measure divided by the sum of the measures, you create a weight. That's inherently 1 in value. SMRs, indirect standardization. You remember, observe minus expected for rate. You end up with something similar to the direct standardization, but it's through a different mechanism. Subgroup analysis, special care, reporting interpretation is required. A priori versus post hoc analysis. Always good to have a priori because you thought about everything and you're sticking to a protocol similar to the idea of intention to treat and per protocol analysis in a randomized clinical trial. So if you have subgroup analysis, you better have thought about them early on when you design your meta-analysis. But post hoc is also valid if you have good justification. Sensitivity analysis, it assesses the robustness of the finding from the meta-analysis. You may repeat analysis on meeting studies with the lowest quality. So it's equivalent to what you do in a sensitivity analysis of a case control that you have selection bias because you lost some information, or a cohort that you lost people to follow up. You have a cohort of 1,000 people, you lost 100 to follow up. You don't know who they are actually because you didn't collect all that we needed to collect before you lost it. You include them in the study, and then all of a sudden you lost them as you're following them up. But you didn't have time to do all the measurements you needed to, or some variables they're changing over time. You only have a baseline. You don't know what happened later on. So you stop playing with those numbers. Say, well, those 100 people are this way or that way. The same thing you do here. with the meta-analysis. You start omitting studies that you consider some problem with it, and say, if I remove those 2 bad studies, how is it my full estimate of the effect size goes? Okay, that's a sensitivity analysis. Okay, such as trimming the extreme 10% of study for each end of the distribution results. For in my study, I had one study that always gave me a huge funnel plot outside everything. So you got to be careful of that. The heterogeneity, random variability, a lot of things playing that I could analyze with or without that study, and I did, and it did not affect too much the overall. So that tells me that's my analysis, my design, and my findings are robust. They are not that sensitive to changing 1 or 2 studies. They are kind of crazy study, it looks like. Publication bias, negative studies less likely to be published often because the investigators don't submit them. It's called the file drawer problem. Put it in the drawer and never comes back to it. Okay, so negative studies less likely to be published. So, therefore, what you have is in excess of positive studies, when they may be even more, they are negative, but you don't know. Step to reduce and identify publication bias, search a registry if they exist. Registries now are very common. Registry for clinical trials, registry for meta-analysis. So there are registry now created by many organizations, including NIH, that you can use to pull the best studies from. Right to scientists work in the field, explicit criteria to exclude small studies, funnel plots, and then identify publication bias. Okay, that's one way to identify publication bias. Fail-safe and calculation. Conclusion recommendations, summarize the key findings that may inform policy, make judgment regarding broad application of the findings. A study is drawing on a limited range of patients in population because the effect modification by age, underlying disease, and generality is going to be compromised. If you're doing a meta-analysis, you end up with very few studies with very few select population. You cannot extrapolate your finds everywhere else. That's the lack of external validity, right? And especially with the issue of effect modification and generalizing it to a bigger population. When heterogeneity among studies is substantial, does a sound explanation exist to account for it? Even though you don't need random effects in this situation, you're kind of controlling those hidden type of bias or confounding, so to speak, but you need to find a way to explain it. That's why I say, read the papers. You may end up with 10 or 20 papers, read them all, make your notes, so you'll be able to end the discussion to elaborate on that. Summary of overview of meta-analysis. By definition, meta-analysis is an observational study because you're observing other people doing studies, subject to bias due to selection, confounding, misclassification. If you select the wrong studies, you're biased. But if you do a criteria like in indicators of quality of studies, you may have a way to control for the bias or to explain what the selection bias is. Confounding, you can also have information on that by doing that indicator of quality score, so to speak. And misclassification may give you proofs, but you actually need to study the papers to understand where the original study. You remember, you know everything about case control and cohort study. You know selection bias, selection bias and case control, the manner in which you select case or control, especially controls. That's your main selection. Cases, both, but especially controls. And then the issue of cohort is how you collect information on the exposure. You need to be precise. You need to be good at that. Usually you are. That's why you create a cohort. You know the exposure well, know how to measure, create exposed and unexposed group. But then you need to control for selection bias introduced by loss to follow-up. You see that? So you know how this study should bias and confound. You know the subject matter. You know things that should be confounded. Can you study dietary intake of anything related to a chronic disease without adjusting for physical activity? I don't think so. Metabolically, they are part of the same equation, right? Energy in, energy out. Okay, so you need to adjust for physical activity. That's some study I've done when I was at CDC, and it's one of the highly cited studies because it proved beyond doubt you cannot do study on nutrition or physical activity without adjusting for the other. So reducing bias, choice of primary results should not be related to the treatment exposure outcome. This is all basic, going back to observational designs, okay? If your manner in which you measure exposure or you select study subject and to study are related to the outcome it's going to affect bias your study. It's a form of selection bias. Allocation subject follow-up assessment results should not be related to treatment. It's going to affect the way you look into the results, especially observations. Heterogeneity is common, but many authors fail to report it, discuss it, explore it. Most good journals would not accept a meta-analysis paper without data on heterogeneity and a discussion. So be prepared to present your I square or Q. Analysis of heterogeneity should be performed by the interpreter cautiously, as with any exploratory analysis. It's not perfect world, okay? And it's not perfect science here. There's a lot of possibility there. Exploring heterogeneity can lead to new insights, okay? I want you to read this part of future application, benefits. It's really a general overview, okay? You can always ask the question, quality score for RCT. You see that? Remember we discussed it? I create a quality score here. 0 to 5, high quality is 3 or more. Reporting on search methods and meta-analysis. And then I'm going to show you a very quick example here in this study. Where is the study? Oh my, sorry. The study disappeared. Give me a second. Can you see it? Is the presentation? Oh, it's not showing. It's not. Oh, I know why. Because it's not sharing the screen, right? Can you call the technician if something's going on? I'm sorry, folks. Give me a few minutes. Why is not showing in presentation mode? Oh, God. Okay. Can you see that? Can you see the presentation? Oh my God! I thought you were following. Sorry, folks. Give me a few minutes. Somebody's here. Can you see it? Somehow I pressed something wrong and took it off. Are you in the site, in the presentation site? Can you see it?
Yes.
Can you hear me? Can you hear me?
Yes.
Okay. Okay, good. Sorry, folks, for this. It's a very quick presentation just to highlight, give a full example. This is a meta-analysis I did. I'm going to skip a few slides because it's for a different presentation internally for a grant that we have this collaborative group and we present. Dr. Yoshida, Yolene Yoshida, was my postdoc for many years. And after that, she became assistant professor in my department, then Tulane University stole her from me. She's now in Tulane. And we did many papers together. I'm going to skip that just to show you that's not different. You see, remember that? You have to go over and find the right way to present it. It all end up being the same way. You need to present how you end up with your numbers. And the goal here is to study the impact of HIT, health information technology, on diabetes. And a secondary goal is the second meta-analysis is the effect of HIT on cardiovascular outcome among diabetic patients. Okay, so many of the same studies from the original meta-analysis were included, but many are new ones because you're focused on cardiovascular event as opposed to just the diabetes outcome A1C. Okay, here the event of interest is anything related to cardiovascular among diabetic person, including A1C change. Okay, now presenting some of the meta-analysis, almost like multiple meta-analysis on the same, it's a subgroup analysis. They were determined a priori. So you have 463 papers with the keywords. You end up with full text articles assessed for eligibility is 57. Once you do that, you exclude 30 because they have full text unavailable. Only include a patient with type 1 diabetes. It has to be excluded because there's type 2 diabetes we're interested in. Involve glucose monitors. You cannot have that because absolute majority of the study did not use glucose monitors. It was a novelty back then at that point. Feasibility trials cannot be included, and no CVD risk factor measurement. So we wanted to adjust for confounding. We needed to have that. So included 27 studies. They're here. Many of the outcomes of interest are there. SBP means systolic blood pressure. DBP means diastolic blood pressure. LDL means low density cholesterol or lipoprotein. HDL, high density lipoprotein or cholesterol. And total cholesterol is total lipoprotein. And weight measurement, body weight measurement, BMI. There are some other, but this is give a flavor. What are the outcomes of our interest? It's almost like specific subgroup analysis a priori determined to be done, okay, including a set of risk factors and other variables we wanted to control for in these original studies, and we did the meta-analysis around them. So, and I'm already skipping a lot of stuff to show you some of the results, so you can see. I'm not going to go in detail here, but you want to present in your papers very similar to, you need to say where this study is coming from. You know, we end up with 3,290 study actually. Interventions were so many, 1977 intervention, and 13 people in the control groups altogether. Mean age range from 45 to 76 years old across the studies. 23 study had even great gender distribution. That means very common number of men and women, both sides equally. 3 studies focused on men and 1 had no gender information, which is crazy because it does affect the outcome, but we decided to include because all the other stuff was there. 20 studies were mobile phone-based interventions, 7 or hybrid. And you need to have a decision. We did before a priori that we will expect that. We say we're going to do subgroup analysis. You see what I'm saying? You need to do a priori. You need to define you're going to do group analysis a priori. Okay? And also, we use this fact also to do sensitivity analysis to see if the quality was influenced by the type of information technology being used to help diabetic patients. So it worked more like a sensitivity analysis. You remove all the hybrid and focus only on those who do text message, only for study. You know what I'm saying? So when you do this, you have all possible combinations. You decide that a priori. You understand the subject matter. I am in the Department of Health Management Informatics, you know, for years. So we know informatics well, and I knew I would expect something like that, even though I haven't read the papers all ahead of time. It was after the meta-analysis that you actually end up with these numbers. 10 studies use a combination of medical care providers to deliver intervention. 4 nurses, 1 physician, only physicians, 4 a combination of personnel, including non-medical personnel, 8. All of these are factors you can use in the analysis. You can create a score variable and throw that in your analysis to adjust for. Intervention periods range from 6 weeks to 1 year, median 6 months. And here's some of the main findings. It's very small. I hope you can bear with me. But these are the difference in means. There is something called, by the way, the outcome variable is A1C change between groups, right? Difference in means between the 2 group intervention, treatment, not treated. So here's the values. The line in the middle is 0. Okay, the line to the left are negative point in terms of A1C. This is a crude type of analysis. Okay. And then on the right-hand side, you see positive numbers. It can go as high as 17.5 or whatever. One of the study has confidence interval. They include almost everything under the sun. It goes from minus 20 all the way to minus 15. Okay, but the average effect was something like 0.5, 0.7. Okay, so this is what you got in a meta-analysis, study by study. And then the last one on the bottom is the average. And the confidence interval, see how the confidence interval is tight? The average across all these studies was actually a negative number, which means 0.56 crude reduction in A1C over an average of 6-month period. And the confidence interval does not include the null hypothesis of 0, because the goal here is like percent change or absolute change actually here. Okay, then I standardize later on. That's the z-value you see there. Okay, the hedge funds is the hedge fund. The hedge G is the value of that thing that is adjusted for all the other elements across all regression. It's a random effect model that includes everything under the sun, and you can see it's negative. The z-value is a negative value. P-value is 0.001, meaning that effect is significant statistically, and it so happens to also be significant clinically. Okay, it's not shabby one. It's pretty decent reduction. It's about 21% reduction, if I could simplify to you. Okay, so the squares indicate study-specific mean difference of the outcome. Horizontal lines indicate 95% confidence interval. The diamond indicates the summary mean difference estimate in the 95% around the 95% confidence interval. The bias adjusted effect size is the hedges, and they provide a confidence interval on that too. So what you have in a study like that, it's a lot of rich information. You wouldn't by reading your original studies, you know, most of them did include the confidence interval of no effect, except for this one here on the left of 1. Okay, but all the others include there's another one, but Logan did not include the confidence interval of no effect. Okay, and there's another one from Coley, the third one down, up from top to bottom. The third one is also did not include. So 3 studies did not include a confidence interval, did not include the null hypothesis of 0. Okay, therefore they are really positive studies. All the others include, I mean, there are no significant statistics, but all of them, with the exception of 3, were below 0. That means there's some effect. When you do a meta-analysis, adjust for everything, it shows you where we need to go, right? So here's the effect on systolic blood pressure. Here's the effect on diastolic blood pressure. It's like a separate meta-analysis, so to speak. They are group analysis, okay? And then you have all the numbers here at the bottom again, is the average. You see how tight the confidence interval. This one here is the effect of HIT on high-density lipoprotein is no effect. The effect is not, it actually is a positive effect. But you want that, right? Remember, this is high-density lipoprotein. It's not low density. So don't be fooled. That positive here is a good thing. It's exactly as a negative is here. Here's a positive. You know, we want to be positive. If it's true, it's great. And it's very tight confidence interval. It is way away from 0. It does reduce substantially it does increase the good cholesterol positively, very high. And then here you have the low density. It does. All of them are significant. The only one that was not significant was triglycerides. The information technology could not help to manage triglyceride in diabetic patients. Okay, and it's also a risk factor for coronary heart disease and for all ischemic heart disease. They say there's a precursor of lipoprotein that goes badly. So that is one you want to control too. He also did not affect the body weights of these people. Okay, so that's a graphic representation. You know, always present kind of the adjusted value, but eventually in the paper you can see crude values too. Here's the same representation summarized way for tables. Okay, you have the difference in means and the hedge from the analysis overall at the bottom, and this one is a special sub-analysis, a sensitivity analysis in which I included, okay, I separate out the standard care controls versus those where it's HIT plus standard care control. Does it affect my analysis? It did affect a little bit, but not much. The main message is that HIT matter. Okay, I don't want to get too much hang up on it because you need to go to the other piece on mathematical. We're going to go quick, but see here we're doing a sensitivity analysis. It's like reading the papers, each one of them. I found out that some of them you can not completely separate the HIT effect or the HIT intervention. For instance, patients were given apps, and some other patients were monitored and fed back and forth through text message. Some others, they have a portal that you download to your computer and you do your checking every day. There are many other ways, but in addition to that, you also have standard care mixed up. So in here, I did a meta-analysis by contrasting only those studies that have standard plus HIT versus standard care. It's a smaller number of studies, 6, 5, not all 30-some studies. And in those, it still replicated the same effect with very few losses, okay? Those were negatives, it's still the same, the triglycerides. But for LDL, HDL, diastolic blood pressure, systolic blood pressure, still significant effect like in the original study. So that's reassuring. You're doing a sensitivity analysis of something that could have affected. It could be an effect modification because I'm mixing the HIT with standard care, and the other one is just standard care control. I was able to derive that from some of the study, but not all. You see the numbers reduced. And in the original, I have one, let me see here. On this one here, I have a lot of maybe 15 papers, 17, 20, 15. Here I only have 5, 6, 4 studies were left, okay? And then below is the comparison, which is similar to the graph. It's for the old studies, 21, 20, 14, 14, 15. So you still see the same find. That's a, what is that? It's a priori conceived sensitivity analysis, okay? And therefore, it reassures you that you find is not by chance alone, it's not biased by not separating out the type of studies, the interventions in the right way. We did, okay? So I wanted to show that so you know that, you know, and I'll give you that. By the way, here's the funnel plot for publication bias. There's one outlier there. You see that? It was not in line with the other in terms of publication bias. Okay, risk bias assessment, it's the same idea, but it presented a different way. And then you have your heterogeneity that I showed to you. Maybe I didn't show in the graph, but there's an I square presented. Where is the I square? Okay, and yeah, here, I squares and Qs. You see that? So I needed to use random effects for most of the analysis. Look at the I square, how big they are in some of the analysis. On the other hand, for triglyceride, I could easily not use, or for HDL, I could just do a fixed effect. I did both, but I presented only random effects model. So let the Q and the I square guide you whether to use, especially I square %, whether to use random effects model or fixed effect model in your meta-analysis using regression, okay? This is a good example here. I did use random effect models for SBP, DBP, triglycerides, and LDL. You know, I didn't use at all for HDL, but I also did the analysis just in case, but it was not significant anyway. And the triglyceride, that could be a toss. I could have used it or not. You probably provide the same result, and I did, and I can't remember, but I'm almost certain. So heterogeneity was assessed using Cochrane's Q and I square. We made a decision a priori that any number greater than, you know, some Q, which is a p-value of 0.5, and I square greater than 50% was really big heterogeneity. Below that, we could have considered not using random effect, okay? But we did, and so it doesn't matter. We have enough numbers in each studies, and many studies, 20, and each of them are very large. So the overall power of the studies were very good, okay? So this is a real example. I wonder if I should leave, yeah. When I copy this into a PDF, I'm also going to leave on the side. It's going to be an extra page with some notes I'm going to put so you can read it. For instance, the note here, I wrote that the heterogeneity observed in BP outcomes in our study may be explained by the wide variation of intervention included. And this helped me to write the paper when I was writing those notes. Intervention under review range from broad, simple methods providing diabetes management suggestions for patient, and I put the reference, the citation, number 72, to more comprehensive intervention permitting timely communication with instructions from diabetes care managers via phone call, SMS, which is, you know, text message, and telemetry devices. Heterogeneity may also stem from variation in intervention design, the type of care or service offered to the control group, differing involvement of healthcare personnel, including different types of personnel, and variation in sample composition. Since clinical and methodological diversity occurs in a meta-analysis, statistical heterogeneity is inevitable, and I quote Higgins on that. So I will leave you these notes. Some of the stuff I copied in the other lecture didn't have notes. So this one, I'll leave the notes so they're precious to me, and I hope it'll be precious to you. It helps me to write the paper. You also can read the papers. And after review this lecture, review this paper, review my notes here, you know how to do a meta-analysis. And I'll actually going to add information on the software that can do meta-analysis for you. Okay, if you feed the software with the right information from the studies and you collect and create the right tables. Okay, so let's finish this and go to the next lecture. How much time do I have on the next one? Oh, already made 12:15? Oh God, it's my watch is team in American time. Okay. Okay. Let's do this, folks. At least 10 minutes on the next lecture. See if I can glean from something, but it's very methodological. Okay. Let me get to it. Freddie may need to help me here. Maybe not. So let me see. Start methods. Which one is this one here?
Sure.
No, it's not. Yep. Okay. Let's see if I do it right. If I do it right.
Right here?
Oh, I have to go here first?
Yeah.
Here and
there. And then you share. Right.
Windows.
I guess it's this one.
Yeah, I think so. Right.
They are watching this, but you can come here. Meta-analysis.
Yep.
That's it.
We have very little time, but it's yours. You can read this. This is prepared by Dr. Similier, puts his number here, his name. Later tonight, later in the afternoon, I'm going to really add more elements to it. This is a key lecture. The one before that, not this one. And I'll add a lot of elements. So you can read that lecture and know how to do a meta-analysis, including I'm going to add information about the softwares and how to feed the software to do it, okay? But here's a little bit of an overview and the example he used on the statistical methods. More on pooling strategy from the BCG, fixed effect, random effect, meta regression. Introduction to the Bayesian methodology. What can I extract from here? We've done that. We've seen that. It's a repeat of what you and I went over, the weighting, very similar to the weighting on Mantel-Hansel for stratified analysis of risk ratio, odds ratios in both case control and cohort studies. These are the key notation. Weight for fixed effect is W. W line is weight fraction for fixed effect, which is basically the proportion of the weight out of the total. And weight star is the weight for the random effects. Weight star line is weight fraction for random effects. That's the proportion of the random effects of the total sum across the studies. And God, I always remember the name of these things. What is that? The Greek letter. Oh God. It's not lambda. No, lambda is whatever it is. That's effect parameter. That's a measure of effect. And the other one is rho, I think, right? That's a variance. Is that rho? I'm terrible with this. I always remember the name. So just remember that little wiggle thing with the square is the variance. The other one with something in the middle, that's the effect parameter. I'll remember and I'll write the names for you. Because statisticians love to label this thing. I never care for that too much. I should have. So this is a cohort study data layout. And you can see, again, where is it coming from? A, B's, and N for this type of notation. You want 1 over A, 1 over B. That's your Mantel-Hansel for risk ratio. I'm trying to make the analogy so you understand where the weighting comes from. In a Mantel-Hansel, I basically have an estimate of the variance of the random variable A. Okay, that's the random variable A. I have A, B, N1, N0, M1, T1 in percentile. Remember, that's a presentation called cohort study data layout, density layout. I don't have A, B, C, D. I have A, B, M1, and N1, N0, T. N1 here is percentile for the exposed group. N0 here is the percentile for the unexposed group. Okay, A over N, N1 is your incidence rate in the exposed. B over N1 is the incidence rate in the unexposed. And M1 over T1 is the incidence rate in the whole city, so to speak, okay, or in the whole community, whatever. It's the sum of the two. So your mental Hans or weighting is basically the inverse of the variance of the measure of your estimate. In this case, a relative risk. It would be 1 over A, 1 over B. And so the variance of the log of the risk ratio is 1 over A, 1 over B. If I take the inverse of it, I'm taking the inverse of the variances to be the weights. And that's the weight used for stratification. So when you stratify across a third variable in a stratification analysis, so you remember from that, from your basic epi that was not with me, then you get the full flavor to understand how the weighting in the meta-analysis done is very similar. Because I'm, instead of doing it across levels of a third variable, let's say I'm interested in the relationship between physical activity in older people and ADL worsening, okay? So I consider an ADL worsening when it reaches 5 or more, okay? And 0 to 5 is still okay. So when I have that situation, you know, and I'm doing that across levels of older people who are of some income level versus a non-income level, so as the third variable is income, I have a contrast between two groups and two strata. So it's 4 groups to extract. So it's a summation across the 4 groups. And the average pooled relative risk is going to be weighted based on that. The variance of that's going to be this baby here, this W that you see is called Mantel-Haenszel estimation of the relative risk, and the variance includes that weighting. Okay, so that's what we do in a meta-analysis, except with a slightly different variance. So I want you to have that flavor. The law of large numbers guarantees that the average of many independent random variables, means and finite variances, is stabilized at their common mean, and its convergence can be obtained through the central limit theorem. And this is from mathematical statistical theory, which is a probability distribution is the function of the summation of the distribution multiplied by the random variable y. Okay, so that dictates the weight fraction range from 0 to 1, because all of them have to add to 1 if you add them up, because they are all probabilities. Okay, and follows a normal distribution. And these are the law of the large number. That's the PDF, which is the standardized normal. Actually, that's a real normal Gaussian distribution, not standardized, sorry. And then you can also do the likelihood function of it. I'm not going to get to the math of it. I'll probably messed up. Simi could do it better than I do. And the log likelihood, understand the principles. You're going to see those things coming back to you if you ever start the logistic regression with me. That I have to show you step by step. And I remember again, every time I do, I relearn it because I can't remember how to derive all of that without making algebraic mistakes, okay? Take the partial derivative. I still remember the partial derivative to get to this, okay? Remember the partial derivative? I hope you do, okay? Similarly, can you also use the MLE to get an inverse variance rate? Yes, you do, and that's what you actually do in the meta-analysis. The principle I mentioned to you about the Mantel-Haenszel and the relative risk is the same. So calculating Q, it's a function of all of that stuff. That's how you calculate Q. Random effect model, again, it's all coming from that, and your 2 ways of calculating methods of moment, which is from mathematics, advanced calculus. You remember the moment, okay? That's how they calculate. Or RMLE is like the likelihood. It's a form of likelihood. It's called RMLE as opposed to the simple likelihood. I forgot what R stands for. Random effect model, that's your final baby. Don't want you to do it that. We only have 5 minutes to go. I just want you to have an appreciation where we're coming from. You can do empirical based, Bayesian, methods of moment, or RMLE. SAS does RMLE for you, okay? When you do the random effects. Here you have the BCG vaccine background. Tuberculosis case increasing. BCG vaccine widely used since 1921. It's not recommended in the US, and people ask the question, is it efficacious? Is it effective? Efficacy ranged from 2 to 90% in different studies. In 1987, Madras trial. In one trial, there were variation. Amazing. What is the policy question? How effective is BCG against TB? How effective is BCG in infants? That's a subgroup analysis. You do a meta-analysis. So there are available 15 studies, clinical trials, and case control, there are 10 case controls. Okay? So he did a meta-analysis of these studies. Statistical methods use the random effect model. They have probably has this reason. Probably I-square is very high, like mine, over 50%, and the Q was pretty large. So study design, randomization method, most of it there, except for the case control. And then you have random effect regression model, quality score included in the analysis. Remember that? Year that started in latitude, where the latitude geographically, you think something to do with latitude could be important. And then you end up with tables like that, BCG, no BCG, case, no case, when you sum across all the studies. This is how it was presented. Okay, you have A, B, C, D, or 2x2 tables, remember, on cohort data. But actually, we're dealing here with mostly randomized trials. You still have A, B, C, D. If your interest is relative risk, not person time, not incidence density, but the risk and the risk ratio or relative risk. So you end up with, across the studies, you have each one of the studies has the A, B, C numbers. You need those. If you cannot estimate that, you drop the study from the meta-analysis, because you need that. And you need an estimate of the variance of each group. And the CD is standard deviation, as you can see. So you have the log of they have the relative risk column and the log of the relative risk column. And then you have standard deviation, you have the 95% confidence interval. Remember that? Okay, so RD, risk difference. A single study categorical data. One of the studies you see, that's the calculation. I gave you that in those lectures early on. You have confidence interval, they include no hypothesis of no difference, that's 0, right? Same thing here. Single study, odds ratio now, okay? And then you have the BCG data. So I'll show you examples to you. And here is the mean differences, the Q found, and everything is produced here. Okay, I'm going to give you a software. They started to do that. This day and age, we can find software that does the job for you if you present the data right. If you enter the data like that, the top part of it, if you have all these numbers to enter and you do this one, sorry, the software will be able to calculate for you. Okay, you don't need to do it, all of that, and do a regression to do it. They will do it for you. Okay, here they find it very similar to how I presented my data, and you know that the 1 for risk ratio is the no hypothesis. If you hit 1, that means there's no association. And the average of the cubes is actually the line on the left that you see here. Okay, that a dotted line, that's the average. And the confidence interval of different study across that line is shown. But they don't present 1 for the line itself. I don't know why. I did present the line. It's easy to visualize where the others are in relation to it. Because here I only present the line, the average of all studies. Okay, then they do a Mantel-Hansel method effect. So actually they're using a Mantel-Hansel. They're not using a regression at this point. It's just the stratify, super stratify analysis. Now they do the random effect. You see, that's a little different. So they use Stata to do, I don't use Stata, I use SAS or the softwares. There are 2 softwares in the market today. I'll give it to you. I forgot their names. And they do mostly regression based. So we're going to go straight to random effects or fixed effect. We don't do stratified Mantel-Hansel analysis. But any meta-analysis is a super stratified analysis. It can approach the same way as you approach stratified analysis of simple cohort, except now you have 10 cohorts, so 10 clinical trials or 20 clinical trials. Okay. Here's the data presentation for the odds ratio. This is probably the few studies that are case controlled. They did separate. They did the trials and the case control. These are the case controls, and these are the trials. So the case controls, the average and the confidence interval showing at the bottom here of the dotted line. You can see the confidence interval do not include the no hypothesis of 1 for the odds ratio. They're all below 1 at about averaging about 0.5. That's a powerful effect, protective effect of BCG against tuberculosis. If anybody in doubt, look at this meta-analysis. But this is from case control. Let's see the other one from non-case controls. You still have a powerful effect at about, I would say 0.7, 0.8, and do not include the no hypothesis of risk ratio 1. So just by look at the risk ratio and odds ratio, I know those studies came from cohort of clinical trials, and this one here came from case control, all these studies. So now you have evidence, powerful evidence from meta-analysis that BCG is a very powerful protector against tuberculosis. Still, CDC has not changed their policy, even after these studies. They need more meta-analysis. The alternative calculations, I gave you Peter, and the mathematics is here. You can read it. We are over time. I know Luiz is saying cut. It's 12:30. Yeah, it's Peter from England. Some cautious about random effect. Okay, recall the random weights. As such, random effects are more likely to be affected by bias to small studies are susceptible, like publication bias. That's why you need a funnel plot. In my study on the funnel plot, I did not exclude that one that was outside, that is a publication bias. But if I had excluded, which I did later on, it did not affect my results. So it's a sensitivity analysis. But you need to look at the funnel plot. The degree of heterogeneity can be so large as to produce different summary statistical inference between random and fixed effect. It is very true if your I-square or your Q's are very high, around 50%. So to be safe, you only do a fixed effect model if it's less than 20% heterogeneity, because then it doesn't matter if you do random or fixed effect, you're going to get the same average score, but the confidence interval will be different for the fixed effect averaging across studies and the random effect averaging across studies. So the BCG conclusion is it seems to have substantial protective effect. Fixed effects odds ratios gives 0.62, random effects give 0.47, because there are some biases. When you do the random effect, you control better for a lot of stuff. They're calling the stratify analysis a kind of a fixed effect. Okay, it is. Strong evidence of heterogeneity, yep, it's pretty high. Need to explore course, so I trust more the random effect than the fixed effect because the heterogeneity is very high. And you see the publication bias in effects funnel plot. Funnel plot are used, I didn't go to that statistic, but it's a standard error of the log of the relative risk of the log, versus the log of the relative risk itself. Is a measure of the random variability within the studies in across studies. So it's also a matter of heterogeneity, but it tells more about apparently publication bias. I need to elaborate on that, and I'll send you a note about that. Thank you. You've been a great audience today. Didn't ask me any questions, but I feel confident that you have excellent material, not perfect delivery, and I apologize for anything coming ahead to you. Dr. Ramos wants to say a few words to you about the end of this short course that we skipped so many steps, but I hope you have had a good time on it.
Thank you, Eduardo. Great course, great classes, and we're gonna keep these videos in these classes for us, and we'll make it available for you in the future. We have to decide where to store all this information. So, but we're gonna have it for consultation in the future. And what I wanted to say is that next week, Dr. Simões will make himself available for 2 sessions of discussion with those who attended the course. We're gonna have a Zoom meeting, and we're gonna pass
a Zoom out. You show up, you're in a meeting. If you don't show up, that's fine. You don't have to.
That's
I'll be available those hours.
But we'll send by email the link for next week. We don't have exact date and time, but you will know.
Ask any question. The goal of the meeting next week, 2 meetings, each of 1 hour to 1 hour and a half. Not fixed. I can prolong the time if needed. For you to ask any question about any of the material in the course, any of the delivery you give. And also, if you don't want to ask about the course, you content with the material, you read it. It's about study you're doing, something that relate to what we did, how you go about this, how you go about that. Like yesterday, there are many questions, 6 or 7 questions, pretty good. So asking those questions, those hours, it's available, it's yours. It's 1 hour. I probably is going to be Tuesday or Wednesday afternoon and Thursday afternoon, 2 days following. We have for an hour and a half. You have me. You can ask me any question. Okay.
Okay, thank you, Eduardo. And I want to give a special thanks to the School of Nursing of UNIFESP, who provided our setting here for the course. And we really thankful to them for making it available, this auditorium, okay? So that's it. Thank you for the audience, and we're gonna be in contact.
Oh, Luiz, let me tell something to the students. If you may, next week you can ask me the question, but every lecture I gave it to you, either as a PowerPoint, as a PDF, we're going to review to make sure that it's harmonize the background of the lecture, the font size, everything, so it looks good. So you have an organized material. If you want to wait until then, I promise next week you get something a little bit better than you receive.
It's only going to be available next week anyway.
Yeah.
Okay, so thank you all. We are finishing here, okay?
Thanks, everybody. Great course, great audience. Ask me more questions next week. Start making notes, okay? Thanks, everybody. We're going to say sayonara now. Bye-bye. What?